safety, and secure signal processing. She has around 100 publications in reputed journals, including IEEE transactions and international conferences to her credit. More than 5 scholars have obtained PhD under her guidance, and currently she has 5 doctoral students.
Thank you, Rehna, for the introduction. With all due respect, may I now invite Professor Deepthi for the session. Thank you.
Thank you for the introduction. I think I'll just keep my video on for some time so that you can at least see who is handling the session. And maybe after that, I can switch off my video. Can I switch off the video?
Yes, ma'am. Yes, ma'am.
Okay. So, good morning, all. It's my pleasure to talk on error control coding strategies. Why? Because of late I'm seeing that people are not paying that much of an attention to the error control coding schemes. Mainly maybe because of the complexity of the field. It's not easy to master the field due to the mathematics associated with that. And sometimes like without error control coding scheme also, things may work, maybe due to that. So I think I haven't talked about error control coding schemes in a talk for last many years. People need only talks on machine learning, privacy preserving machine learning, cryptography. All those are becoming more hot these days. So I'm happy that I could talk about error control coding schemes now, because as 5G and 6G challenges are growing, it's of great importance that one should have good expertise in designing and decoding error control coding schemes to build a efficient communication system. So, error control coding scheme is becoming more of an inevitable block in communication system now. It was not so earlier. Because if I ask you, you have to build a communication system to send your speech in a local area, a network within your campus, may not be that necessary that you think of a power efficient error control coding scheme. How to design or decode an error control coding scheme may not be your concern, because the overall redundancy in the data itself may support the error correction, automatic correction, and you may not feel the need. So generally, I always tell in my introductory class in my error control coding course that it is not an indispensable block. Error control coding scheme is not an indispensable block in a communication system. If your channel is good enough, and if you're sending data only within a small premises, and if your data is having enough redundancy in itself, then you may be saved without a error control code block within your communication system. So then now I said it's becoming more of a hotter topic of research. Why? Because we know that we are making use of wireless communication channels for supporting all the data transfer. And wireless communication channels have all their issues like multipath propagation, interference from other communication devices, from other carrier frequencies, many things, many types of interferences you can think of when you say that your channel is open, like a wireless channel. So wireless communication itself imposes more challenges on maintaining the required performance or quality of service as demanded by the user, so that one will have to think about channel coding schemes. And these days, things are even more complex. We are making use of our communication devices for anything and everything. See, if you have to listen to some audio or video, you're making use of your phone, and the data is getting downloaded to you through the wireless open channel where all types of errors can happen. But you cannot tolerate delays, you cannot tolerate errors. Not just multimedia or just your entertainment. It's more of a like finger burning experience. If you feel that when you key in the credit card number or bank account number, it's going in error, it's more critical. Not only that, we are making use of, or we are moving into an era of using your GPS for guiding you over the road. So if it shows you, yeah, in many scenarios it is already notorious for misguiding you, but still, if it is misguiding you, things may become even more difficult for you. So you know that now each bit is so important for you. Each bit you send over the channel or somebody else send over the channel for you is very crucial for you. You can't afford to have errors in that. So it's highly essential now to have a powerful channel coding so that your data will be delivered to you correctly without any errors. So the channel coding schemes, okay, what are coding schemes you're familiar with other than channel coding schemes? When you say channel coding scheme, other than channel coding scheme, what other coding scheme you have in communication system? You have source coding as well as channel coding, isn't it? Looking at the various blocks in your digital communication system, you start from the source, the information source we say, and in many cases the information source could be analog. So you need to have digitization block first, which you call it as a waveform coding block. So the first block, when I say please try to visualize, unfortunately we cannot interact and I don't have a board on which I can draw. Basically I'm a board and chalk teacher and it's very difficult for me to even deal with PPTs. So try to visualize what I'm telling. So your digital communication system has got the initial, the front end block as the source, which is your information source. The moment you say it's an information source, you know that it is characterized by a statistical distribution. Now, the data could be analog or it could be digital by nature itself. If it is analog, you have to convert it into the digital form for all the processing, high-end processings that you want. Now, this bits that you get after digitization, they need to be compactly represented. That means you know that spectrum is one of the most costly resources. So if you want to improve the spectral efficiency, the first requirement is that you need to minimize the number of bits required to represent the source. So that coding is always a mapping. Coding means what? It's a mapping basically. So that coding which helps you to reduce the redundancy in representing the bits coming out of the source is source coding. And the efficient source coding scheme will be looking at the statistical characteristics of the source to optimize the number of bits required for representing them, bits delivered by the source. Now these bits which are coming at the output of the source coder need to be sent over the channel. As we said earlier, the channel is erroneous, it's having noise additions, it's having multipath fading, all those effects. So you are sure that your bits will get corrupted at different rates at different positions. So the next requirement is you have to introduce some redundancy in this compact representation of source which you already got in such a way that you'll be able to correct for the errors at the receiver side and you can retrieve the data effectively at the receiver. So the way in which you can add redundancy in this source coded data so that you'll be able to efficiently recreate the data at the receiver side. That mapping is called a channel coding. So why is it called channel coding? While the other one is called source coding. The first coding that you said, the requirement for that is an efficient representation of source. That means minimizing the number of bits required to represent a source. And this efficiency is governed by how well you make use of the statistical characteristics of the source in representing it. Wherein, in the case of channel coding, in the case of channel coding, which is also coding is always a mapping, as I said earlier. It's always a mapping from one sequence of bits to another sequence of bits. Or could be sequence of symbols to another sequence of symbols. So in the case of source coding, it is done in such a way as to optimize the representation source or to remove the redundancy in representation source, where in the case of channel coding, it is in such a way as to facilitate the errors that has happened over the channel. So the best way to perform that mapping would be to look at the statistical characteristics of the channel so that you will have a very efficient, that means bandwidth efficient representation enabling error correction. That means you can think of adding so much of redundancy so that your error correction will be improved. But then when you're adding redundancy, you're sure that you're wasting some bandwidth. That means your spectrum, the costly resource that you are causing it to get deprived of. So that also cannot be done. So how to look at the channel characteristics in such a way as to help error correction, at the same time save bandwidth to the best extent possible. That's what is taken care of in a channel coding scheme. So you may feel that, okay, in source coding scheme, I'm removing the source redundancy, and in channel coding scheme, I'm adding redundancy. So why can't they be combined? Why I need to first remove the redundancy and then add redundancy in channel coding scheme? So there is what I said. Source coding scheme will be efficient if it looks at the source statistical characteristics in such a way as to optimize the representation. And the channel coding scheme will be optimal if it looks at the statistical characteristics of the channel in such a way as to ensure error-free reception. So that's why they are separate. One looks at the source statistical distribution, the other looks at the channel statistical distribution. So channel coding is all about adding controlled redundancy in representing the source output. So when you think about adding redundancy, you may feel that is about repeating it. But just repeating it won't help you, is what we have seen. Just repeating is just consuming the bandwidth. It's not helping you that much to correct for errors. So you have to add the redundancy in a controlled way as to facilitate error correction. So there were schemes which make use of the properties, mathematical properties, or the various algebraic structures which will enable error correction. So that is why, basically, as I said in the initial part of my lecture, that channel coding, if one has to think about designing or decoding, we have to be familiar with the corresponding mathematical structures. And I don't think that with this 1.5 hours, I can go into the depth of the mathematical structures which we are basically making use in the design of decoding of the codes. But you all know that we are operating in Galois field, finite field, which is a basic algebraic structure used for designing the codes. So we construct the words of transmitted messages in such a way that those words are elements of a vector space, so that you can make use of the properties of that vector space at the receiver side for correcting the errors. So basically the question will be, how do I map my message words to the elements of a high dimensional vector space so that At the receiver side, the mapping from the received word to the transmitted word could be done by making use of the vector space properties. Basically, that is the encoding process. So in that particular encoding process, you can either treat the message symbols as running symbols, or you can treat them as blocks of symbols. So
Ma'am, may I interrupt you?
Yeah, please.
Ma'am, is it the fourth slide now?
Yeah, I have not moved.
It is not moving that.
I told you, I'm basically a board and job teacher, so
Okay.
you're finding it difficult?
No, no, ma'am. There's some comments
Okay.
received from
Yeah,
multiple
okay, okay. And let me see, I'll try to move as per slides after giving the introduction.
Okay, ma'am.
And is it too much for you, like the introduction, you all know this and I don't have to say this?
No,
Then
no,
I
no.
can move on to.
No, ma'am. You
No,
can
yeah, please.
comfortably move.
Yeah, no, no, you may interrupt me, whichever way you want, I can go like that. Only issue is, I told you, no, in which way I want to turn my lecture, for that I won't be having the slides. Otherwise, if it is a board and choke, whichever way you want, I'm comfortable in all areas of channel coding, whether it is just the fundamental mathematics, whether it is on the design of the hardware structure, whether it is on the decoding, algorithmic complexities associated with that. Anything is okay for me. But the thing is that the moment we say that is PPT, we have to restrict to some particular pattern. That's why.
Yeah, it's okay,
so,
ma'am.
yeah,
No
okay.
problem.
Yeah. So so what I told you is, in constructing the code, you are making use of the vector space properties. So it's a mapping from the set of source symbols to a larger length or larger number of symbols. So there in that mapping, what I said is, you can either think of taking a running sequence of symbols and mapping to another running sequence of symbols, which gives rise to non-block codes. Or it could be more easy for you to treat them as a block of symbols of a particular length, and obviously mapping to a block which is of higher length through the encoding operation. So there, when you are treating the symbols as a block, we call it as block codes. And what is this linear term coming there? Linear block codes. The block codes, when you say that, I said it's a block of information symbols getting mapped to block of coded symbols. And obviously, the length of the coded symbols words is larger than the length of the information symbol block words. Length of a word means number of symbols present in the word. So length of channel coded symbol is, or channel coded word is, say n, which is greater than the length of the source coded symbol, say k. In a general scenario, we call it as an n, k code, nk code, where n is greater than k. N is the number of symbols present in a word, and k is the number of symbols present in the information word. So it's about mapping a k length or k block length word to a n block length word. And linearity is coming from the property of the words that we should, or the space in which these words are contained, in such a way that the error correction is facilitated. I told you, we make use of mathematics for constructing the set of code words. So we use the mathematics in such a way that the set of code words satisfy certain properties which facilitate error correction. So the basic property we make use generally is those of a vector space. So vector space, you know that vector space is closed under linear combination operation. That means scalar addition, scalar multiplication, and vector addition. So that basic property is what we make use, so that at the receiver side, you can map from the received word to the transmitted error-free coded symbol. So we have to bring in certain properties in constructing this vector space. So that way, the simplest linear block code that you can construct to have particular error correction property is Bose-Chaudhary-Huckingham's DCH codes, which you may be familiar with. That could be the simplest binary linear block code that you can think of to introduce the required error correction capabilities. DCH code, Bose-Chaudhary-Huckingham codes. So there you can bring in the required error correction capability. And it is a good coding scheme. If you just, as I said, if you just want to think of transmitting your data to a small distance without much of a problem of channel errors, DCH codes suffice. That is enough. But then that is not enough if you feel that your spectrum is very costly and you want to have a spectral efficient communication, we can think of going for Reed-Solomon codes. Reed-Solomon code is basically a DCH code, but the only thing is that it's not binary, it's non-binary, or it could be a binary extension. So obviously, when you move from DCH to Reed-Solomon, what you get is improved spectral efficiency. Like for a given redundancy, you have the best error correction performance in Reed-Solomon's code because they are maximum distance separable code. That means in a given construction, you can have the maximum separation between the code words. But always there is no free lunch. So when you're moving from DCH to Reed-Solomon codes, though you have it improved spectral efficiency or improved error correction performance that you can think of, it comes with increased structural complexity in encoding and decoding. So that is where we were for quite some time, till like codes like low density parity check codes came into picture. And polar codes is a new addition which came recently. The corresponding, as I said, the corresponding non-block versions were also becoming popular when DCH and Reed-Solomon codes were widely used in the implementation of various communication systems. Corresponding non-block code which was popular was convolutional codes. Again, turbo code can be considered together with low density parity check codes and polar codes. So what is the difference? Like DCH code and Reed-Solomon code, I said. And at that time, you had the corresponding non-block version convolutional codes also running. People were making use of PCH codes, Reed-Solomon codes, and convolutional codes for their purposes. So when we moved on to low density parity check codes or turbo codes, what was the beauty? Like they offer error correction performance close to Shannon limit. They could provide error correction performance close to Shannon limit. I hope you are familiar with Claude Shannon, who is basically the father of information theory. So it was Shannon who set the bounds on what could be achieved through source coding and channel coding performance. His source coding theorem set the bounds on what could be performed in source coding, and his noisy coding theorem set the bounds on what could be achieved through channel coding schemes. So see, I don't know what way to communicate with you. It is a monologue, I know, but with 69 participants, I daren't ask you to interact. Do anyone know what is noisy coding theorem, or can you say it out? I will try my luck once. Can anyone tell me what is Shannon's noisy coding theorem? Okay, so I'm not lucky enough. Okay, so what Shannon's noisy coding theorem says is, when your information rate, as I said earlier, in a channel coding scheme, you are basically adding redundancy. That means the information rate is not full. Like each one bit you are transmitting is not fully packed with information because you have diluted it. You have added redundancy to that. So each bit is now not containing full of information. It is only containing partial information. So that partial information is basically the fraction. That is the information rate or code rate you call. Or code rate or information rate is number of bits which are effectively transmitted divided by the number of bits which are actually transmitted. I told you earlier, for an NK code, K is a number of information bits which you are effectively transmitting, where N is the actual number of bits which you are sending on the channel. So K by N is a code rate. So what Shannon said is, yeah, you have to add redundancy to take care of the disturbances on the channel, noise on the channel. But you don't have to dilute it much. You just maintain the code rate in such a way that it is just less than the channel capacity. Even then, you can devise a methodology in such a way that you can obtain absolutely low probability of error. That's what Shannon said in his noisy coding theorem. So till that, actually, we were not knowing, okay, to what extent I have to add redundancy so that I can consider myself as lucky enough to extract the data without much of an error. But Shannon said, look, you don't have to add so much of redundancy. You just have to add redundancy in such a way that your rate of information, it is sent on the channel. That is what we call it as code rate. For 10K code, you know that K is a number of bits which are effectively transmitted. I sent only K information bits, but I extended or expanded to N bits, where N greater than K. So the number of bits which are effectively transmitted on the channel is only K, while the number of bits which are actually transmitted on the channel is N. This K by N, you need to make it just slightly less than the capacity of the channel. Then you can get an absolutely low probability of error is what Shannon said. So the beauty of Shannon's theory is that he said it in 1940s and all over the years, even in 2008 when Edel Ariken found polar codes, he was trying to achieve that bound. So something which was said in 1940s by Shannon, researchers were trying to achieve it over the years. So bounds are set there, and all the design concepts in Shannon coding theorem are trying to achieve it. So that is the beauty of Shannon's noisy coding theorem. So turbo codes, low density parity check codes, polar codes are attempts to realize the Shannon bound. So how was it possible? I said BCH code, Ray-Solomon code, convolutional codes were our code, Shannon coding schemes for quite a long time. So what was the reason for that quantum jump in the performance from the families like BCH code, Ray-Solomon codes, convolution codes, etc.? They were also good codes. They are also good codes. So by then, the other codes like LDPC, Polar, Turbo, they belong to another family, we say. Their capacity achieving codes, we say. What is this capacity achieving? That's what I said. Shannon said your code rate need to be just less than the capacity. Still, you can get absolutely low probability of error. But all our BCH code or Ray-Solomon code, the code rate is much, much lesser than the capacity. Code rate is much, much lesser means what? K by N. That fraction is very small. That means we are adding much of a redundancy. That means we are wasting much of a spectrum. That is not needed. You can still have very low, absolutely low probability of error is what is said by Shannon. So where was the gap? The gap is in the decoding. Basically, we were not having powerful decoding schemes for BCH codes or Ray-Solomon codes or convolution codes. That was the issue. So we were able to implement only minimum distance or maximum likelihood decoding, wherein you know that the minimum probability of error decoding is possible only in the case of maximum a posteriori probability decoding, MAP. Maximum a posteriori probability decoding is that decoding method which can provide you absolutely the probability of error. But PCH codes or Ray-Solomon codes or convolutional codes do not have a structure which support MAP decoding. So that was the issue. So when it was realized that there is a decoding, the gap between the performance of a practical code and the ideal Shannon code is due to the inefficiency in decoding. So then how to make that efficient decoding possible was the question. To make that efficient decoding possible, we have to think about improving the structure of the code. So that is how LDPC, Polar codes, and Turbo codes are designed in such a way as to facilitate MAP decoding. So that's the beauty of those codes. So this is about the various Shannon coding schemes, the history or evolution of that. So we all know that we are now making use of LDPC, Polar, or Turbo codes for an efficient error correction. So at least now you're happy that I moved on to the next slide. So now, okay, it was about the advances in Shannon coding schemes, I said, but it is about the advances in Shannon coding scheme used about mobile communication standards as well. So we know that we could see a quantum jump in the performance of the mobile communication standards from 2G to 3G. From 3G to 4G, maybe we didn't visualize that much of a quantum jump. but from 2G to 3G, that performance change was highly noticeable. So what actually made it possible? What mechanism basically made it possible for jump to the performance from 2G to 3G is nothing but the adoption of powerful turbo codes or powerful decoding schemes for convolutional codes. Basically, improving upon the decoding schemes came with the convolutional decoding. And with the convolutional decoding, to improve upon further the decoding performance, how to improve the structure of the convolutional codes were thought about, and thus turbo codes were invented. So convolutional and turbo codes were deployed in 3G schemes, and the performance jump from 2G to 3G was highly noticeable, and that was made possible only due to the powerful channel coding schemes. Now you understand. Okay, initially I said channel coding scheme is not a must. Yeah, it's not a must. You still can receive the data. It's not a must. But if you want to receive the data with good quality and with large number of data received with good quality, yes, you want a very efficient and powerful channel coding scheme. Without that, it is not feasible only. Yeah, Priyanka, you raise your hand knowingly or unknowingly? I see a raised hand. Priyanka Kale has raised hand. Is it knowingly or unknowingly? I think she has done it unknowingly, maybe. I'm not able to hear.
Ma'am, happened by mistake.
Okay, no issue. Yeah. So that is the power of the channel coding scheme. Though it is not a must, it is the thing which help you to move on to higher W. So now I said from 3G to 4G, actually the channel coding scheme didn't change. It's only the methodology, the way in which the convolutional turbo codes were made use of. That slight change only they did from 3G to 4G. So they adopted the hybrid ARQ techniques in the case of bringing the improvement in the performance of 4G compared to 3G. But now we say when we are moving from 4G to 5G, again we expect a quantum jump in performance. We are not happy with what we are having now. We feel that mobile phones will replace everything. Mobile phones will replace your PC, mobile phones will replace your TV, everything. So everything should be done through mobile phones. That has become the inevitable part of your life, you know, and you expect everything to be done through that. So obviously, we once again now expect a quantum jump in the performance when you move from 4G to 5G. So what 5G vision is migration to millimeter wave spectrum. Yeah, it is easy to vision, but we know that when we move on to the millimeter wave spectrum, there are fast fading and shadowing effects waiting for you. You would have already seen these things in the previous sessions, maybe. Similarly, we expect 1,000 times the capacity compared to the present LTE system over this unstable channel, which is offered by the millimeter wave. Same way, we think of getting everything, like I said, your mobile phone has to replace your TV. So we expect your high powerful video streaming. For that, you need to have very high throughput and very low latency to have the proper video streaming without breaks. But we know that the high bandwidth that is demanded by various video applications need to be supported. That means spectrum, which is a constrained resource available to you, should be able to support the high throughput and high data rate, which is demanded by your applications. Yeah, but it is heterogeneous too. Like on one side, you think about the high throughput requirements and the high low latency requirements imposed by multimedia or video streaming. On the other side, you think about IoT. You say that each and every sensor, your sensor fit in your refrigerator, sensors fit in your car which you are driving, anything and everything around you will be talking. So all those sensors are sensing the environment or data from the environment and sending it over over your same communication channels given out or laid down by 5G. But there the data rate is much lesser than the data rate required by the live video streaming. So that is the issue with, or that is a requirement and vision and challenge of 5G. That means it has to support a wide range of requirements, starting from a very few bits of data rate demanded by the sensor data acquisition systems to a high data streaming requirements of video. So supporting all, yes?
Ma'am, what is the difference between shadowing and fading?
See, you had a course on wireless. Please don't ask me doubts on wireless. We will restrict to channel coding, okay? You had sessions on that, right? I'm not going to talk about the wireless communication channel impairments, okay? If you ask about the channel coding schemes, I'll be happy to say, because I have only 1.5 hours and I'm here to talk about channel coding schemes. Yeah, so the requirement is to address the heterogeneity in applications, starting from, as I said, the video streaming to the sensing. The requirements, the rate requirements are highly varied. All these need to be supported. So as I said, the channel coding scheme is an important thing which decides the performance. I said no earlier, the quantum jump in the performance from 2G to 3G was made feasible due to the adoption of a powerful channel coding scheme. So same way here also, channel decoder is the thing which decides the performance. So that is why we are so much interested in choosing the channel coding scheme suitably for 5G. It has to support the varying rate requirements. It has to retain the complexity requirements, and it has to retain the QoS, quality of service, performance requirements. So that is where we are now. We have to have a channel coding scheme which supports all these requirements. So you may have seen that the channel coding scheme suggested for 5G. As I said earlier, as already I said, that turbo coding scheme is a channel coding scheme that is used in 4G and 3G as well. So turbo coding was used in 3G or 4G. 3G it was used at that time. There was a quantum jump, and at that time there was a change in all the communication devices which are implemented in various systems. But then when we move from one generation to this another generation, the issue is that compatibility need to be retained. Like with your 3G phone, you should be able to work with all the services offered by 4G. Similarly, your 4G phone, you need to, or you feel like utilizing the services supported by 5G. So there's a need for compatibility. But at the same time, to support the varying code rate requirements and performance requirements of 5G, it is felt, or it is researched and found out that turbo coding may not be enough. That's why they are moving for LDPC codes and polar codes. And as per 5G new radio standards, LDPC codes are preferred for data, while polar codes are preferred for control information. And why that is so also, I can tell you, or you'll be knowing later. It is easier to tune LDPC performance, code rate, or performance parameters to meet the varying requirements of varying data rates of applications. But polar, bipolar is not for data, that's what I'm saying. See, polar, the issue is that when I said about source coding and channel coding, I told you that source coding exploit the source statistical characteristics, while channel coding exploit the channel statistical characteristic. That's what I told you. But up to polar codes, none of the codes are designed making use of the channel characteristics. They are exploiting the channel characteristics in the decoding, but not in the construction of the codes. But polar codes are designed in such a way that their structure, their design is evolved from the statistical characteristic of the channel. So it is heavily, the best design of a polar code is heavily dependent upon the channel statistical characteristics. That is a disadvantage of polar codes actually. LDPC codes are comparatively having a higher complexity in encoding and decoding than polar, or rather polar is low complex and having a low complex encoding and low complex decoding. But the issue is that the design is evolving from the channel characteristics. And when your channel is almost stable, yeah, polar is reliable. But when your channel characteristics are widely changing, polar is not that reliable. That's why, or at least it is not yet tested and confirmed. It has not yet tested and confirmed its performance. At least that much only I can say. Maybe that's what, that's a research. That's one of the researches going on. How to make your polar code designs almost like not independent of, at least robust to the channel changes. On one side, we say that polar code design is, can we say LDPC for source code and polar for channel? No. LDPC is not for source coding. LDPC is for, both are for channel coding only. I told you, no. LDPC, only thing is that its design is not evolving from channel characteristic, but its decoding is using the channel characteristic. I hope that is clear. I'm not sure who has answered the question. Yeah, Anupam Tiwari. Now, Anupam, LDPC based, yeah, LDPC based source coding is there. In fact, you can use it for distributed source coding, LDPC codes, wherein you make use of the syndrome for, say, in the case of sensor, when you say that when you're deploying sensors in a wireless sensor network, you know that almost all the sensors are capturing the same data, or the data captured by different sensors have got a large amount of commonness, correlation among them. In that case, we have a thought like, why do you send each and every individual data separately, encode it and send? Instead, we just encode the data of one sensor, and what way the other sensor data is differing from that. For example, you think about a seismic data. That means you're you're capturing the earthquake, whether the earthquake has happened or earthquake is prone, or etc. The seismic data you're capturing and sending it using multiple sensors deployed in a particular area. So you're sure that there is a large amount of correlation among the various data samples taken by the various sensors. In such scenarios, what could be done is one of the sensors will be sending the original data and the other will be just sending what is different from this. There, LDPC can be used for source coding. But LDPC is not a code developed for source coding. It is used for correcting the errors. And decoding make use of the channel characteristics. It's not encoded. LDPC is decode oriented and polar is no, I don't know. I didn't understand the question. LDPC is decode oriented and polar is channel characteristics. No, both LDPC polar, not just LDPC polar and turbo codes are designed to support map decoding. That's what I said earlier. With BCH, Reed-Solomon and convolutional codes, they are also powerful codes, but the gap was in decoding. They were not having the structure that support map or maximum a posteriori probability decoding. You know that map is a decoding which gives you minimum probability of error. So with the decoding scheme that we used in BCH, Reed-Solomon and convolutional was derived from maximum likelihood decoding. So LDPC, polar and turbo have a decoding scheme which is enabling map decoding. So there we make use of the channel characteristic. But polar is in such a way that the design itself is coming from the channel characteristic. So if the channel is highly unstable, it's very difficult to design a popular polar code which can ensure a good performance over varying channel characteristics. It's not yet tested is only what we can say. Polar was invented only in 2008 by American. So it's yet to be tested for robustness against variations in the channel characteristics. Okay, if you are good in the design of, or good in the development of polar code, you can think of doing that. And any research in the design of efficient encoders and decoders of polar codes is still a hot topic. Maybe probably because of that, it is used for only control information, because there is no need for supporting that type of a high throughput, low latency, varying throughput requirements, etc. for control information as compared to data. So LDPC is well proved and tested now because it has come in 1990s. No, so it is well proved and tested now. Maybe because of that, LDPC is used for data and Polar code for control. I hope that answers you, Anupam. Yeah. So what it says is there's a total change in the channel coding scheme from 4G to 5G. As I said, from 3G to 4G, there was not much of a change. There was only some change in the decoding type of the way in which the channel codes are utilized. So when you change it totally, it comes with a cost. No, you have to retain the compatibility, means how you redesign the chips coming in your mobile phones to support this change in the channel coding scheme and the corresponding encoding and decoding. So that's why I said once again now channel coding schemes are now attracting attention of researchers, because to make it feasible to have the high performance 5G communication, you have to think of developing the efficient encoders and decoders for LDPC and Polar. And people all over the world are working at it now. So that is why now this research is widely looked at, or it is attracting the attention of researchers recently. So what is low density parity check codes? So I said it is supporting map decoding, etc. No. So what is so special about it? The name says it is a low density parity check codes. So where is that low density coming into picture? Or basically, what is this low density? Density means nothing but the number of ones in the parity check matrix, H matrix of the code. So the number of ones in the H matrix representation of the codes is very low. That's what is called the low density. As I told you earlier, see, anyone who knows the basics of channel coding, you know that there is a pair representation for any channel code. The representation coming from the generator matrix as well as the parity check matrix. So the generator matrix and parity check matrix can be derived from each other. If you have a generator matrix, you can get the parity check matrix. If you have a parity check matrix, you can derive the generator matrix, because those two span the null spaces. So if you know the basis vector spanning one vector space, you know the base vector spanning its null space. Stack of basis vectors of code space is nothing but G matrix, wherein stack of basis vectors of null space is H matrix. So they are derived from each other. So H matrix facilitates error detection or decoding, wherein G matrix facilitates encoding. That also you know. So obviously, I told you the power of LDPC codes is from its power of decoding, or rather, its structure supports a powerful decoding. So that is where this low density comes into picture. The type of decoding used in LDPC, which is called the belief propagation, that we will see after this. So the belief propagation works, or it will converge only if the parity check matrix has got a low density. Only if parity check matrix has got small number of ones. Otherwise, the type of powerful decoding called belief propagation used in LDPC codes won't work. This is what I said. It is making use of channel characteristic in decoding, and to facilitate the powerful decoding, the structure of the encoder is designed suitably. Or encoding is supporting powerful decoding, which was not so in the case of BCH, Reed-Solomon convolutional codes. We know in the case of deriving turbo codes, basically it's a modification of convolutional codes. So convolutional codes is modified in such a way as to support the turbo nature in decoding. What is a turbo nature in decoding? That itself is a basic principle used in low density parity check codes also. Basically, as I have written, uh, low density parity check codes was originally invented by Gallagher. It was his PhD thesis in 1960s, which he presented in 1960s. But at that time, it was not noticed only. Why? Because Gallagher couldn't convince his readers that it is basically low density parity check codes can provide a better performance than other like BCH or Reed Solomon. He couldn't say it out clearly what is the beauty of LDPC codes. That was the issue. The beauty of LDPC codes was realized after invention of turbo codes. That is why we say that LDPC codes was basically rediscovered in mid-1990s by McKay. Basically, this rediscovery happened only after the evolution or introduction of turbo codes. It was in turbo codes, the concept of utilizing estimates of a priori probability for implementing MAC detection was made use, or it became like accepted that it is not impossible to implement map decoding. Basically, the issue was this. Everyone knows theoretically that it is maximum a posteriori probability decoding that improves error performance. But maximum a posteriori probability values basically demand the a priori probability values. A priori probabilities of the data, which is transmitted from somewhere. How do we arrive at those values? How do a receiver can expect to get the a priori probabilities of data symbols which are being transmitted from a remote transmitter? That was the issue. So everyone thought that no, it cannot be feasible. No one at the receiver side can think of getting the a priori probabilities. So forget it. We will implement maximum likelihood decoding, which is a suboptimal decoder, and we'll be happy with the corresponding error performance. That was the scenario when we were using in 1990s, when we were using DCH, RS, and convolution codes. But later it was realized that it is feasible to estimate the a priori probabilities from the other received data. A priori probability of a particular transmitted symbol will be estimated from other related data. You are basically generating a relationship through encoding now. So you are using that relationship and you are using the information about a bit that is conveyed through another bit which is connected to it. How do we connect in the encoding channel coding? You know that you have a parity check equation, and all those bits which are connected through a parity check equation are basically connected. So one symbol can say something about the other symbol. If you say that a particular parity check equation is not satisfied, obviously they are interconnected. We don't know exactly which symbol has gone in error, but one symbol, if you are decoding, it can say something about the other symbol. So it is the interdependencies between these symbols that we can make use, and we can derive or we can estimate the a priori probabilities. But the only thing is that when you encode the word, you have to pay some attention in such a way that unbiased information about a symbol is given by some other symbol. So that is the way I see. The structure of the encoder need to be designed in such a way as to facilitate the estimation of a priori probabilities. So this was found in the invention of turbo codes. So you can see that in turbo codes there are two convolution coders. They are assisting each other. One convolution coder outputs can give some extra information. We call it as extrinsic information. These are very catchy words. Extrinsic information. Extrinsic information is the extra information that we can get about a bit from another bit. That extra information can be used to estimate the a priori probability of a data. And this a priori probability can be used in the decoding. This is the thing. This thing was understood by the invention of turbo codes. So then McKay realized that the LDPC codes, which is already developed by Gallagher in 1960s, also have that particular beauty in its structure. It is basically able to provide, it is not just an LBC. When Gallagher presented it, it was just an LBC. It's just a linear block code. So then it is not just an LBC. It can also support this maximum apostrophe probability decoding is brought out by Mackay. That's why it is said that LDPC is reinvented by Mackay. And after that only, yeah, LDPC is also similar to Turbo. Both of them are able to achieve a performance close to Shannon limit was understood. So of course, the one which gained popularity first was Turbo. So Turbo was used in your 3G, not LDPC. But later it was realized that maybe LDPC can outperform Turbo in terms of encoding, efficient encoding and decoding. So that is why now it can support also varying rates. That's why now we are thinking about adopting LDPC in 5G. So it is a sparseness of H matrix that facilitate the powerful decoding in LDPC codes. If you make H dense, then this decoding won't converge. So that is the beauty of this low density. So the low density facilitate maximum apostrophe probability decoding for channel coding. Yeah. So the two types of LDPC codes that you can think of constructing are regular and irregular LDPC codes. So in a regular LDPC codes, what we say is that, of course, it has got a uniform structure. That means number of ones in a column, all columns have got equal number of ones. Similarly, all rows have equal number of ones. I hope you know that H matrix, what I told you earlier is H matrix is nothing but a stack of basis vectors of null space, of code space. Or each row of an H matrix is nothing but a parity check equation. I hope you know that. Each column of an H matrix corresponds to a code bit, and each row of an H matrix corresponds to a parity check equation. So number of ones in a column need to be same, and number of ones in a row need to be same, means it brings in uniformity in constructing the code. So if you have got such a uniform structure, you call that code as regular, wherein if you don't have the uniformity, you call it as irregular. Both regular and irregular codes have got their own advantages. The regularity obviously brings in advantages in implementation. The structure is easily adaptable to varying code rates, parallelism in implementation, high speed of performance, etc. They are advantages of regular codes. Wherein irregular basically is more close to Shannon's random codes. So obviously irregular codes have got a improved performance. Wherein improved performance means improved error correction performance. Error correction performance is better in the case of irregular codes, while in the case of regular codes, the beauty is that it could be easily implemented in hardware through parallelism, because one subunit can be replicated, or you can introduce parallelism in implementation, and you can bring in low latency, high throughput implementations for a regular H matrix. So that is why we cannot say that we will always go for only regular structure, or we will always go for only irregular structure. We can't say. Also, irregular has got that advantage that I don't know. Like in the case of multimedia communication, it is so all bits are not equally important. We know that. For example, if you are thinking about an image transmission, we know that those bits in the background are not as important as those which are in the highly sensitive areas. So we can think of providing varying levels of protection against error at different regions of images when you are encoding it. So if you want to provide different levels of error correction at different portions, we need to have an unequal error protection. So there also we can think about using irregular codes. So if you are having in some parity check equation, more number of bits are included, means the corresponding the number of ones in those corresponding rows will be higher. So that is about the irregularity, isn't it? So irregular codes have got all those advantages. They are having better error performance. They can support unequal error protection. All those advantages are there, but regular structures have got the advantages of having an efficient hardware, low latency, high power efficiency in the implementation. So this figure can give you an approximate comparison about regular and irregular performance. You can see that, generally what you are seeing at the left-hand side is the Shannon limit. What I told you is, Shannon said that the moment you bring in a code rate which is less than the capacity, you can have an absolutely low probability of error. So Shannon says that that EB by naught, what you are seeing there is the one corresponding to your EB by naught means the SNR. So you just go it slightly only to that level, then itself you are able to get an absolutely low probability of error is what he says. So that sudden jump in the performance is what is approximated by the practical codes. So that particular sudden jump is called the waterfall structure, wherein the dotted line is the actual uncoded BPSK performance. It is a very shallow dotted line. So from there to that vertical line shown by Shannon is a gap that is to be addressed by the various practical channel codes. And obviously, you can see that your practical LDPC codes are very close to Shannon limit. And there you can see irregular codes are much closer to Shannon limit than irregular codes. But they have the issue of error flow. What is meant by error flow is, it could be seen that in some constructions, after a particular BER is not improving even if you improve the SNR. Generally, what we expect is that when SNR is improved, error performance is should anyway improve. No? But in the case of irregular LDPC codes, there is an issue that some bits get trapped during decoding due to the non-uniform number of bits associated with the number of package equations. After some point, even if you increase SNR, the error performance won't improve. So that is called error flow. And error flow is more visible in the case of irregular codes than regular codes. So that is about a comparison of irregular codes and regular codes. You may need both depending upon your requirement. And the way in which H matrix was constructed. So obviously I said design should start from H matrix, because you have to design the code in such a way that you have a sparse number of ones or low number of ones in H matrix. No. So the design of LDPC code is starting from the design of H matrix. And for the design of H matrix, you have three types of methods like semi-random, fully random, and fully structured. And the one suggested by Gallagher was a semi-random. That was also one of the reasons why Gallagher's method was not noticed. Gallagher couldn't say a systematic method for generating an H matrix for varying code rates. He just suggested one semi-random method. It was neither structured, it was not properly random also. So people were not able to understand how to expand that method for varying rates. So that was also one reason why Gallagher's method was not noted. After that, there is a possibility of developing it as a fully random. As a person from cryptography, I can say that is a randomness that you can utilize for embedding secrecy in the encoding of LDPC codes. There is a possibility of developing fully random H matrix in such a way as to maintain the maintain the sparsity in its structure. The moment you are able to satisfy the sparsity in the H matrix structure, yeah, you are able to bring in the corresponding powerful decoding into the LDPC. So it is only required to maintain the low density. And to maintain the low density, you can start from fully random, you can have semi-random, or you can have a fully structured. And what we do is to encode. For encoding, you need to have G matrix. So starting from H matrix is designed in such a way as to retain the sparsity. From H matrix, you know how to convert to G, because you know G into H transpose is 0 is a basic relationship connecting the encoding and parity check matrices. So from H, you can of course derive your G, and from G, you can develop the code word. Basically, that is the encoding, but there is an issue with that when you go for the direct encoding. H is sparse, but when you what way you convert into G, you basically know that the relationship between G and H is, if G is a form IKP, Ik is identity matrix of size k by k. Ik p, if G is of that form, then H is of this form, P transpose I n minus k. So using that duality relationship between G and K only, G and H only, you're converting from parity check matrix to encoding matrix. So that for that you have to first do Gaussian elimination on H matrix, or that means you have to apply row transformations. But when you do those row transformations on the sparse H matrix, the sparsity in H matrix will be lost. You will not be able to retain the low density of ones in H matrix after applying the row transformation. That is an issue. So that is why we have two methods of encoding. We have a direct encoding as well as an indirect encoding. In direct encoding, as I said, from H matrix, you just apply the Gaussian elimination, convert it into that either In minus k P transpose P or P In minus k, whichever way. P transpose In minus k or In minus k P transpose. Convert into that form, and from there you get the G matrix, and using the G encode. And generally we go for systematic encoding. That's why here I have used CSSG. S is a systematic information bit part and the additional parity part. So that way you can implement the encoding, but the issue associated with it is that G matrix may not be sparse, it may be dense. So when you generate S into G, G is a dense matrix. So when you think of a hardware implementation and all, it's a means power consuming implementation. Why? Because G is dense means you have so many ones there. So when you have so many ones there, when you multiply and add it, there's a need for large number of multiplications and additions. So it is called the dense vector multiplication. And that dense vector multiplication basically calls for high structural complexity and power consumption. That's why we have a corresponding indirect method of encoding also, which is called RU method or Richardson's Abang method, wherein instead of doing the complete Gaussian elimination on H matrix and converting it into that form, that means what I said, In minus k P transpose or P transpose In minus k into that form, what is done is H is converted into an approximate lower triangular form, that is ALT form, as shown here, wherein H has m many rows. M is n minus k, the number of parity check equations, and it has got n many columns. N is a number of symbols in a code word, that is length of the code word. So that is divided into so many A, B, T, C, D, E submatrices, wherein T is lower triangular. So this is called the approximate lower triangular form for H. So convert it only into that form. That you don't have to do much of a row transmission. That is the advantage, so that it will not cause density in the structure. So then from that H alt, that means approximate lower triangular form, you can convert into an HT, which is an encoding H matrix, by pre-multiplying with a matrix like this. E, you know, E is this submatrix, T is this submatrix in H. So these E and T are used. So minus E into T inverse. Minus, when you are in binary, minus is plus itself. So minus E into T inverse is a submatrix here. This is identity matrix. This is null matrix. This is again the identity matrix. So this multiplied with H alt, what will happen? H alt is ABT, CDE. So when you are multiplying with I0, it comes as A. The top portion will not change, no, because it is getting multiplied with I into whatever, A, I into B, I into, that way it comes. The bottom one is getting added to 0. So the first row remain as such. So that is ABT itself, here itself, because it is getting multiplied, it is getting multiplied with I and 0. Then in the bottom part, it is getting multiplied with ET inverse and I. So obviously, for the last row, what happens? For the last row, it is CDE. That is when it is getting multiplied with TE, when it is getting multiplied with minus ET inverse and I. TE is a column, this column, no? So minus E, T inverse T will be minus E plus I into E. That is again E. So minus E plus E, it becomes 0. So it will bring in a 0 here. CT and DT are the corresponding transformed portions of C and D. C, sorry. Yeah. C and D will be correspondingly transformed to CT and DT by applying this minus E into T inverse and I multiplication. So that way, H alt is converted into an HT encoding form. And from this HT, basically, how do we get the parity part? Your means code word is a systematic code word. One part is as such the information part, the remaining is a parity bit. So you have to derive only the parity part P. So how to derive the parity part is the only question that you have. Now, when your H matrix is in this form, you can say that this n minus m is what? M is n minus k. That is the number of parity equation. So obviously, n minus m is n minus k. That is k. So this submatrix has k many columns. So obviously, this is a part corresponding to systematic part. This one is one set of parity. This one is another set of parity. So the code word representation which I have written earlier as SP, now I can write it as SP1, P2. That means the parity part itself divided into two subparts P1 and P2. So you know that S is as such the information bit. Your duty is only to develop the parity part P1 and P2. So what you do is you multiply it. That means you know that the validation expression is H into C transpose is equal to 0. No? That is a validation. That means if your code word is means received word is a valid code word, that will be orthogonal to the null space. That means H into C transpose will be 0. So H into C transpose is 0 is a code word validation. So you have to construct code word C in such a way that when operated with H, it brings a 0. So C is a code word that you have to design, S, P1, P2. In such a way that when operated with H as H into C transpose, it brings in a 0. And H, you know now, is your new HT, ABT, CT, DT, 0. So when you are multiplying this with C transpose is nothing but your S transpose, P1 transpose, P2 transpose. So ABT into C transpose will be A S transpose plus B P1 transpose plus T P2 transpose 0 to 0. Second row CT DT 0. CT S transpose plus DT P1 transpose 0 to 0. So from the second equation, you can see that this is known to you, this is known to you, this is known to you. S is nothing but a systematic information bits. That's known to you. CT and DT are parts of your H matrix that is known to you. So from that, you can solve for P1. Once you are solved for P1, you know S, you know P1, you know A, you know B. From this, T is also known to you, you can solve for P2. So it is about solving for the parity part from the code validation expression. That's the encoding method, which is a indirect encoding method for LDPC code. So these two methods are popularly used now. This is what I said. So these two methods are popularly used now in the encoding of LDPC codes. But if you're thinking about very low latency and high power efficient implementations, what type of structure that you use? Encoding could be either direct or indirect. But then I told you earlier, to do the encoding, you have to first develop the H matrix. How do you develop H matrix? You know only one characteristic now, that H should have low number of ones, low density. So how to develop, how to design such an H matrix is now your question. And for that only, you have the powerful quasi-cyclic LDPC codes. I am not telling that this is an exhaustive method of designing LDPC code. You have multiple methods for coming up with a design for H matrix, but quasi-cyclic LDPC codes have become popular because of their feasibility for low complex implementation and a highly systematic way for constructing H matrix. So the two beauties of quasi-cyclic LDPC codes, QZ LDPC codes, the way they are popular. So QZ LDPC codes have got the beauty is that they are very suitable for a low complex hardware implementation. Plus, they yield a systematic method for the design of the H matrix. So how we go about designing the LDPC codes? First, you have to come up with a design of H matrix. design of H matrix in such a way that it has got a low density of ones. Once you develop the H matrix, you know you can either go for a direct method of encoding, which I said earlier, wherein from H matrix you convert into G matrix through Gaussian elimination, and from G matrix you generate the code word as C is equal to U into G. Or that method has got a disadvantage that you are getting a dense G matrix, and with that you have to multiply the U, etc. So what you can do is you can start the encoding directly from H matrix as well. That is the RU method, indirect encoding method. But for those two methods, initially you should have an H matrix. So H matrix in the quasi-cyclic LDPC codes have got the quasi-cyclic structure. What is a quasi-cyclic structure? It has got a cyclic structure in sub-matrices. It's not an overall cyclic matrix, but the sub-matrices of H matrix are cyclic. And you know what is a cyclic matrix? Cyclic matrix is a matrix where each row is a cyclic rotation of the row above it. Like your identity matrix. Identity matrix is a typical example of a cyclic matrix. Each row is a cyclic shift of the row above it. So like that, in a quasi-cyclic LDPC code, each submatrix as given here, Aij, is a cyclic matrix. It's a circulant. So that allows you to have a highly efficient linear encoding, partially parallel structures. That's why you're able to get a power efficient, low latency implementation using QZ-LDPC. The structure itself tells, you know, it has the beauty that each subunit is a cyclic thing. And cyclic, you know, each row is a cyclic shift of the other row. So encoding is very easy because the way in which you encode one row could be easily used in the other row also, because rows are so heavily related. I don't know whether, do we have a break? Organizers?
Yeah, ma'am, if you want, we can give a.
I
10 minutes
need
break.
at least a water break. I need to drink water.
Yeah.
So 5 minutes.
Yeah, okay, fine.
Yeah.
We'll wait for 5 minutes.
Yeah.
Audience, water break for 5 minutes.
Hello. I hope I'm audible.
Yes, ma'am.
Yeah, can I continue?
Wait a second. Yes, ma'am. Please continue.
Yeah. And so what I will tell you is now my time is limited. So I will see what are things I can see. So one method of generating quasi-cyclic LDPC code is what I'm just telling. You need to construct an H matrix which is quasi-cyclic. That means in subsections it is cyclic. So how you can think about constructing? There are many methods. By making use of the concepts of abstract algebra, there are many methods. And what I'm outlining here is just one method, wherein what you're doing is you're just picking two integers A and B from a finite field, Galois field M, where M is a prime. So order of a integer is nothing but the smallest integer for that particular number, such that a raised to that particular integer is unity. For example, order of a is k means a raised to k is 1, and k is the smallest integer for a such that this happens. Similarly, order of b is j means j is the smallest integer for b such that b raised to j is 1. That means b raised to 1, b raised to 2, etc. b raised to j minus 1 are distinct integers from GFM. Similarly, a raised to 1, a raised to 2, etc. a raised to k minus 1 are distinct integers from GFM. A raised to k is unity, means a raised to k plus 1 is a raised to k plus 2 is a square, etc. It repeats. So k is a order means you have k many distinct integers that could be developed from A. Similarly, j many distinct integers that could be developed from B. So using this, you can construct a matrix P like this: 1, A square, etc. So the advantage of choosing the k means the order k is that A square, etc. a raised to k minus 1, all of them are distinct integers. Similarly, b square, etc. all of them are distinct integers. So the first row is developed as 1, a square, etc. a raised to k minus 1. The next one is multiplying this first row with b. So b, a, b, etc. Next is again multiplying this second row with b. Like that, you go up to b raised to j minus 1, because you know that b raised to j is 1. So you'll go back to the first row. So you have distinctly this many rows and this many columns. That means you have k many columns and j many rows in this P matrix. This is not H matrix, in this P matrix. Now from this, actually this P is not used anywhere. You just need the integers developed in this matrix. That means 1, a square, etc. No, those integers which are written in this matrix only are needed. P as such is not needed in constructing H. So what you are doing, H is constructed as I1, IA square, etc. IA raised to k minus 1. That means this 1a square, etc. a raised to k minus 1, no, that one. Similarly, BAB were the second row. So this is IB, IAB, etc. Now what is I1 and I2? I1, I2 are nothing but identity matrices whose rows are shifted to left by 1 position or 2 positions respectively. That means IA means identity matrix whose rows are left shifted by A units. IA square means identity matrix whose rows are left shifted by A square units. So each of these submatrices is nothing but developed from the identity matrix. So obviously they are cyclic. How much they are shifted is decided by the elements that you have picked. For example, considering the finite field GF7 and picking the integers 3 and 2, you know that 3 is having, 2 and 6. And you know that 2 is having an order 3. Why? Because 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, and 8 is nothing but 1 in GF7. So 2 cube is 1. Similarly for 6, 6 raised to 1 is 6, 6 raised to 2 is 36, and 36 is 1 in GF7. So B has order 2 and A has order 3. So you can have only 3 many columns and 2 many rows. And the elements are 2, 2 square, 1, 2, 2 square, 1, 2, 2 square. Multiplying that with 3, that with 6, 1 into 6, 2 into 6 is 5 in GS7. And 4 into 6 is 3 in GS7. So I1, I2, I4, I6, I5, I3. This is a H matrix. So obviously the size is what? Each identity matrix is a P by P matrix. Here that P or M or whatever, the prime, basic prime of the GF Galois field is 7. So each I is an identity matrix of size 7 by 7. So here you can see that M, that means number of rows in H matrix is 7 plus 7, 14. And number of columns is 7 plus 7 plus 7, that is 21. So it's a 14 by 21 matrix. So correspondingly, this H matrix can define what code size. N is 21, N minus K is 14. So it's a 21 common 7 common 21 comma 7 code, NK code, rate 1 by 3. So this H matrix can define a rate 1 by 3 QC LDPC code. N minus K is M, that is here 7 plus 7. Each identity matrix is a P by P matrix, where P is a prime with which you have started the Galois field. So each identity matrix is an IP, sorry, I P by P. Now how many positions the rows of that identity matrix should be shifted is what we have defined through this. So this gives you one method of constructing QC-LDPC. Now, I told you the beauty of low density parity check codes is that it supports iterative message passing decoding. This is the nature of LDPC code, or we have said that earlier that the process was first invented in the case of Turbo. It's that structure which facilitates maximum a posteriori probability decoding. So basically what is done is a priori probabilities are estimated from the information that we receive about a bit from the other bit. What are those other bits connected to a bit? The other bits that are connected to a bit are nothing but the bits which are related through a parity check equation. So in the case of LDPC codes, the message passing decoding is done. That is also done like Turbo code I told you, is done to estimate the a priori probabilities. Now, this extra information that you get about a bit from the other bit is called extrinsic information. So what we do basically is, once you construct a code, there is no exactly a minimum distance that you can find out from the code structure. That is a disadvantage. BCH and others and all, they have a daemon defined for the encoding structure. But for LDPC and all, there is no a particular daemon defined for an encoding. So what you do is you have basic minimum properties which can ensure a good daemon. And now if you want to improve upon daemon, what you do is you take a close look at the decoding process. And you see how the probability density values are evolving over decoding. How these messages which are passed between the code words or code symbols are changing over the decoding process. This is called density evolution. These are the keywords which you will see when you look at the recent papers on LDPC or polar code. Density evolution is nothing but how the probability density function of these varying extra information values are changing over the iterative decoding process. So if they are getting modified in a favorable way, then you say that your design is good. If it is not moving in a favorable way, that tells you that you have to modify the design. So that is why this extrinsic information transfer chart, which is called exit charts, are important in the design of a code. So you first come up with a crude design, then you look at the decoding, you closely track the way in which the probability density values are getting modified during decoding. That is called density evolution curves or extra information transfer chart. Both are nothing but the same. Exit chart is nothing but the DE chart, density evolution chart. So you see the way in which the messages which are getting passed between the bits are changing. So from that, you can think about bringing in modifications in the design. So the basic decoding of LDPC codes is done on a tanograph. You may be already familiar with the trellis, which is used in the decoding of turbo. Turbo decoding is explained by making use of a trellis, which is a sequential, which is developed from state table with time instances that you know. So similar to that, LDPC codes decoding is explained with a tanograph. Tanograph is nothing but a bipartite graph. A bipartite graph means a graph in which one set of nodes cannot be connected among themselves. There will be only two sets of nodes, and edges or connections will be only from one node from one set to another node from the other set. The nodes in the same set cannot be connected. Such graphs are called bipartite graph. So that was invented by Tanner, so they are called tanagraphs. So basically, tanograph is the structure which is used for describing the decoding of LDPC codes. The two sets of nodes which are used there are specific to our H matrix structure. What I said, each row of an H matrix is correspond to a parity check equation. No, so corresponding to each row there is a node, and that node is called a check node, because each row of a H matrix is a parity check equation. So corresponding to each parity check equation, there is a node, and that is called check node. Now, each column is corresponding to a code bit. So corresponding to each column, that there is a node, and that is called a variable node, or also called bit nodes. That is a code bit. So variable nodes are corresponding to each code bits, and check nodes are correspond to each parity check equation. Now, as I said, it's a bipartite graph. Edge is a connection from one node to another node. That means one code word cannot be connected to another code word, but one code word will be connected to a parity check equation. So there will be a edge from one variable node to a check node. Similarly, a check node to a variable node. Now, degree of a node is nothing but the number of edges which are incident on a node. For example, if it is a parity check equation, that means if it is a check node, how many code bits are participating in that parity check equation will decide the degree of that check node. So that will decide the number of edges incident on it. So that will decide the degree of the check nodes. So now there are two ways in which you can look at the decoding. If you want a simple implementation, you are not able to provide a very high complex decoder structure. You want a very simple decoding. In that case, you can think of hard decision decoding, wherein soft decision decoding give you much better error performance with the additional complex decoder structure. So the name itself tells you that hard decision means you try with just ones and zeros. When you see, you know that when you receive a data from the channel, it is a soft value. It's a voltage level. It's a voltage value. It's not going to be 1 or 0, no, binary 1 or 0. You get a voltage sensed from the channel. So when you receive a signal, it's a soft value. So before applying it to the decoder itself, you apply a thresholding. If it is above a particular level, you consider it as binary 0 if you are using BPSK. Or whichever way. If you're thinking about just BPSK, you say that if it is below a level, it is binary 1. If it is above a level, it is binary 0. So if that is the way you are doing a hard decision, making a hard decision there. So that means you sense a voltage from the channel. That soft voltage value is not used as such, but you are taking a decision. You are applying a thresholding there is taking a hard decision about the bit and using these bits in decoding. If that is the case, it is called a hard decision decoding. If you are not taking a hard decision there, rather you take those values as such, and these soft values are used as such in the decoding, it is called soft decision decoding. Obviously, soft decision decoding is a powerful decoding. Hard decision decoding is used only when you cannot afford to have a complex decoder at the receiver side. So you have a bit flipping algorithm as a hard decision decoding version, and belief propagation algorithm as a soft decision decoding version. But bit flipping algorithm is also basically a belief propagation algorithm. And to explain the basic idea, I will use a bit flipping algorithm. There also one belief is getting propagated, and what we say that H should be low density, etc. will be clear once we explain that hard decision decoding bit flipping algorithm. So we'll see how that is being done. So bipartite graph that I have said. And what is said here is there will be a connection from a check node, ith check node to a jth variable node. Ith check node to a jth variable node means jth code bit is participating in the ith parity check equation. Jth code bit is present in the ith parity check equation means hij is 1. Then you can expect an edge from ith check node to the jth variable node. So that is a way in which the bipartite graphs are constructed, like this. See, this is a structure correspond to this H matrix. See, this H matrix has got 4 rows, 1, 2, 3, 4, 8 columns. It's a rate half code. It should be correspond to a rate half code. N is 8 and N minus K is 4 means K is also 4. So now this is a parity check equation. This row corresponds to a parity check equation. This means that C0 is not participating. The 0th code bit is not participating in the first parity check equation. So this is the node. These are the nodes correspond to the 4 parity check equations, and these are the nodes corresponding to each of the code bit C0, C1, C2, etc. C7. So you can see that C0 is not participating in the F0, the first this parity check equation. So there is no edge from C0 to F0. From C0, where you have connection, where you can see ones in the first column. You can see ones in the second and fourth. That means C0, you have an edge to second parity check equation and fourth parity check equation. For the this particular column, you can see that the first and second, this code bit participates in the first and second parity check equation. That means first and second parity check equation. This one participates in second and third. That means this is second and third. This is the way the bipartite graph is formed. So this is a bipartite graph. This is one set of nodes. This is another set of nodes. There is no edge between this. There is an edge only from one of this to this. Now you can see that the cycles that could be formed within this bipartite graph decides the error correction performance of the code. You can see a cycle is nothing but starting from a node, passing through edges, coming back to that. So in a bipartite graph, the smallest length of a cycle is 4. Because see, you are going here. From here, you have already gone to a check node. From that check node, you go to another variable node. From that variable node, again, you go to a check node. You go back to the variable node. That means there are 2 code bits where both these code bits are participating in 2 parity check equation. These 2 are participating in this parity check equation. These 2 are participating in this parity check equation as well. Then you have a cycle of the smallest length 4. Such a thing is basically just 1 minute. I'll take a call. Guru, I'm in a talk. I'll call you. Okay. Okay. Yeah. Yeah, so here you can see that you have the shortest length cycle. That means cycle of length 4 is present. But that is a bad property as well as a good error correction performance codes are considered. Basically, we call girth as a shortest length of the shortest cycle. And we should design the codes in such a way that girth shouldn't be 4. That means the length of the shortest cycle shouldn't be 4. That way you should design the code. So one of the basic properties that we say is that no 2 bits should be participating in the same 2 parity check equation. That's what I said. No, in such cases only you will have a cycle of length 4. So that should be avoided. See here, C2 and C5. C2, no, this one. C2, C3. These two share the property that see. They are having 2 ones in common. Here it has a 1, here also it has got a 1. So this should be avoided. No 2 columns should have more than one in common is what we say to avoid a girth of 4. No 2 columns should have more than one in common. So if that happens, here also you can see this can also give a cycle of length 4. So cycle of length 4 should be avoided in a good code. So as a basic property in the construction. So in bit flipping, what is being done? So what is the beliefs that are getting propagated is what we are trying to see. So assume that we have received a word 1001001, this particular one. Sorry, this is transmitted word, and this is the one which is received. That means there's a flipping in the second bit. Now, when these bits are received, what is done is in the step 1, these received symbols. It's a hard distance decoding, I told you. So it is not these ones and zeros which are received. You receive a voltage level. Those voltage levels are hard thresholded, and these values are used as such. Now these values, what it does is, it is transmitted to the connected check node. So what is done here? Here you can see that, see, all these nodes, that means the check nodes have got the corresponding beliefs as the received bits. So this has received a 1 means it is believing that that 1 is correct. This has received a 1 means it is believing that that 1 is correct. So what it will send is, it will send that beliefs to the connected node. It will send that 1 to this node. This will send that 0 to whatever, 1 to this node, etc. So the initial step is that the bit nodes or variable nodes send the beliefs to the connected check node. Now the check node takes the belief received from all the connected nodes. So for example, this particular check node that has got a connection to C1, it has got a connection to C3, C4 and C7. So it receives the beliefs from all these nodes. It processes all these beliefs. Now, what way is the belief correct? Is the belief which is already sent from C1, is that correct? How does it check? It removes C1 and consider all other bits which are connected to it. That means to update the belief for C1, it looks at the beliefs received from C3, C4 and C7. Now, using the beliefs received from C3, C4 and C7, it updates C1. For example, if it is receiving, see if it is receiving a 1 here and a 1 here and a 1 here and a 0 here. That means odd number of ones it is receiving, you assume. So there a 1 was received here, then a 0, then a 1, then a 1 was received, assume. Now it removes this and consider the beliefs received from these two. It has got an even number of ones. You know that a parity check equation will be satisfied when there is an even number of ones. So it has already got 2 ones here and a 0 here. So as per its belief, this bit has to be 0. Then only its parity check equation will be satisfied. So basically what is done? Each code bit sends its hard thresholded value, 1s or 0s, to this as belief. Now this fellow receives all the belief. It updates the belief of this particular bit based upon the beliefs received from the other symbols. In the hard thresholded way, this is nothing but just the even number of ones. So if this is 1, this is 0, then this is 1 and this is 1. Then to recalculate the belief corresponding to this, it checks, it removes this and looks at the beliefs received from this. So it's for it is already satisfying the parity check equation with the 2 ones received from here. So this thinks that this has to be 0. So it sends back the belief that it believed this bit to be 0. Now this got a belief. Like this, each code bit get a belief from the parity check bit or check node. Now this node then updates its belief. It has got its own earlier belief. Now it will receive a belief from this check node. It will get a belief from this check node, what it should be. Similarly, this fellow gets it has got its own belief earlier. It receives a belief from this. It receives a belief from this. So it has to update its belief now. They say that I should be like this. They say that I should be like this. I thought that I'm like this. This is the thing. Now I have to take a decision what I should be. So that is the response that is to be calculated from the code bit. Next, in the next step, this particular code bit, it takes the belief received from this, it takes the belief received from this, it has its own initial belief, it looks at the received beliefs and its own initial beliefs and calculates its response. That will be computed, that response will be computed and sent back to this bits. This is a belief propagation. Now you will know why the low density is important. It is like your own decision making. When you are having an issue in your life, when you have got a problem, what you do, you will be able to take a clear decision if you ask unbiased friends. If you discuss with unbiased friends who are not biased with previous information, if you ask them, they will give you their own beliefs. Then from their beliefs and from your own initial belief, you take a decision. You will be able to come up or converge to a proper, fair decision only if you are asking a very small number of your close friends. If you keep on asking to a large number of friends, obviously you are not going to conclude or converge to a proper decision. This is the basic idea of low density. If number of ones in H matrix is high, that indicates that each code bit means number of edges in this H matrix, in this bipartite graph will be very high. That means the number of beliefs which are coming to each of the code bit will be very high, and the decision making will be totally cumbersome. The decision making or the belief propagation is not going to converge at all. So what is that is the extrinsic information that you are getting. The belief about this bit is obtained from the other bits. That is the extrinsic information, and that is the thing which is helping you to update the a priori probability. So this is the crux of belief propagation. Each variable node, that means code bit, sends its belief to the check node. Check node corresponds to parity equation. That processes all the beliefs corresponding to the connected nodes, those mean the code bits which are participating in that parity equation. It computes the belief correspond to each bit considering only other bits. Considering other bits which are connected to it, it calculates the modified belief correspond to each bit and sends to it. Now each code bit gets the belief back from all the check node. That means all the parity equation which is participating. It updates its belief by considering all the communicated beliefs and its own initial belief. So this is the process of belief propagation. And in the hard decision decoding, that is bit flipping, the beliefs are given in terms of binary values. Wherein in the case of, wherein in the case of some product algorithm, the beliefs are just the probabilities. These probabilities are initially the likelihood values, and these likelihood values will be updated in terms of the a priori probabilities values in terms when you get the probabilities correspond to the other bits. So that is the extrinsic information that you are getting. That means the probability that this particular bit is 1 given the corresponding observed value. Probability that a bit is 0 given the corresponding observed value. These are nothing but your a posteriori probability values. These a posteriori probability values, you don't know exactly. What you have is a likelihood value, and likelihood value from the other bits will be communicated to you as your a priori probability values. So from that you will get an estimate of a priori probability values, which will help you to implement the map. And it facilitates a converging and efficient decoding only if the density is low. If the density is high, it will never converge. Such a belief propagation will never converge due to the large number of beliefs which are participating in that. You will not even be able to take a majority decision. You will be totally confused. So the same way, the bits will also get confused and the bits will not converge to a decision making. So that is the idea of belief propagation decoding. Now these basically for the easiness in implementation, you can, all these are sums and products that you have to implement. So to make the implementation of the products easier, you go to log domain. So you have a log domain belief propagation, which is a basic log domain sum product algorithm. Belief propagation basically computes the responses, no? So when you are computing the responses, it is nothing but the products and sums. That's why it is called a sum product algorithm. So it is getting log domain, log SPA you have, then there is a minimum sum. That means you have basically the product that you see here, when you convert into log domain, it is sum. And all these are probability values. So it's a negative. So in a negative sum, it is the smallest negative value which carries the sense of it. So you need not sum it together. You need to just take the lowest value and take the sense. These are all techniques to improve the implementation easiness. or reduce the implementation complexity, you go for min-sum. Basically, the optimal algorithm is some product algorithm or its corresponding log domain version. But since it has to go for a large number of summations, we go for a suboptimal min-sum method, wherein you don't take all the values, you take only the smallest value. That means the highest probability. Highest probability gives you the largest negative value. So that value only you take, that is a min-sum. You take only the sign of it in the major decision making, that is offset min-sum. And basically, it is an offset min-sum applied in the layered way is a turbo decoding message passing, which is the current trend in the LDPC decoding. Wherein what you are doing is, see, in each column, if you have got 3 ones, means what? Each column corresponds to a code bit and it participates in 3 parity check equation. So like this, it's a uniform, it's a regular code. So each column is having 3 ones, means you divide the entire H matrix in 3 submatrices. And in each submatrix, you perform the decoding so that you can have some parallelism in the implementation. One layer is implemented as one hardware structure. So you do the updation of the messages. You are already seeing that belief propagation is nothing but updation of messages. So you do the updation of messages in one layer and then get the corresponding updated message from the other layer. So this helps or this facilitates parallelism in implementation. That's why turbo decoding message passing. Turbo decoding message passing is nothing but the same sum product algorithm. It's suboptimal version, offset min-sum in a layered fashion. So that is basically used in efficient implementation of LDPC decoding. I'll just give you a basic about polar codes and stop. Or do I have to stop here? Either I can stop here or I can give you basics of polar codes and stop.
Ma'am, if it would be better if you could conclude because we 11.
Yeah, it's already time. Yeah, it's already time. I know. So yeah, so I told you LDPC is not making use of the channel characteristics in its design. It is making use of the channel characteristics only in the decoding. Here you see these probability values are the channel probability values. So that is used only in the decoding. It's not used in the encoding. So that is what I said initially. All codes, including Turbo, LDPC, none of them make use of the channel characteristic in its encoding. Wherein Polar directly takes the channel characteristics in its encoding. Of course, it has got the advantage and the performance improves. But the issue also, you know that a wireless channel is highly unstable. The probability metrics, which you call it as a probability that one bit is 0 or 1 given a observed value. Those things are going to change drastically due to the channel instability. So that is an issue with the polar code, and that's why polar code is not yet used, even though it is low complex and is having a better performance compared to LDPC codes. It is not yet used in data information passing because it is not, means encoding and decoding is not yet developed to tackle the robustness issues for the channel variation. That's why I say there is a large scope of research. Research in what? Research in the efficient implementation of channel encoders, decoders for both LDPC and Polar. And in the case of Polar, how to make the Polar encoding robust, performance of the Polar encoding robust against the channel variations is also something that you need to look upon. So those are the major research challenges in the latest channel codes. With that, I'll wind up so that I can give you a 2-3 minutes, I think 7 minutes for queries.
Thank you, ma'am.
Yeah.
The floor is now open to questions. We're running short of time, so we'll take a couple of questions.
I think there are no more queries. Only the queries that posted earlier that I can answer.
They have asked some questions in between. Probably that
Yeah.
may be the reason.
Yeah.
Anyway, it was nice. It was nice session. You took us through the various techniques and research.
I'm sorry,
topics.
maybe like I spent some time on the initial portion. That's why I couldn't cover Polar, but I thought that introductory part is needed. That's why. Sorry.
Yeah, no, that was okay, I think. Because we are all, most of the candidates are in communication only. So it was a nice session. And you took us
I can share
through some
the slides
topics.
and those who can read those questions, Polar codes, and they can listen to some talks from Andrew Tangraj sir, IIT Madras. He has talked about the encoding and decoding of polar codes, and Edgar Ariken, who has invented polar codes, his own slides are also there. So someone who is interested in polar codes, they can look into that. And of course, I can share this PPT.
Okay, thank you. Ma'am, as a token of gratitude from College of Engineering and also on behalf of all the participants, I extend you an e-memento. Please accept this one.
Thank you so much. Thank you so much for your time. And at least the initial few interactions, thank you so much for that. I hope I didn't bore you at least.
Okay.
Okay, thank you.
So, okay, thank you, ma'am. And for the participants, the feedback link is posted in the window. Please do mark your attendance also. And Suresh Nair sir have joined in. We'll be checking the connections and all. Probably you can join at 11:15. The next session will start at 11:50. Thank you, ma'am.
Okay, so shall I leave? Thank you.
Yes, ma'am. Yes, ma'am. Thank you. Please.
Sir, good morning, sir.
Good morning.
Sir.
Good morning. Yes. So I will just try to share my slide and see.
Yes, sir. Visible.
I don't know.
Okay.
Yeah, fine, sir. Full screen now.
We will join by 11:15.
Yes, sir. 11:15 we start this session.
Okay.
Actually, we have 148 participants registered for this program.
Oh.
And out of that, 92 are from outside state.
Okay.
So in this adult AST programs, the registration is through the AST portal. So everybody can register through.
Okay. Okay.
Checking Rehana, are you there? Rehana. Rehna, have you joined?
Yes, sir.
Rehna?
Hello. Yes,
Yeah,
sir.
okay,
I'll
okay,
join.
okay. So, good morning. Let us start the next section. Next session. Let me invite Rehna to read out the profile of Dr. Suresh. Thank you. Over to
It's
you,
my
Rehna.
honor. It's my honor to introduce Dr. Suresh Nair, sir, to the distinguished participants of the FTP. Dr. Suresh Nair, alumnus of Department of Electrical Engineering, IIT Bombay, has spent his initial career at R&D Lab of Ministry of Information Technology, Government of India. He then joined SFO Technologies, Nest Group as Global Chief Technology Officer, heading the technology strategies. Under his leadership, many novel products in healthcare, communication, industrial, aerospace, and defense domains were designed, and many are finding excellent market acceptance globally. Dr. Suresh Nair is presently Chief Technology Advisor to Foundation for Innovation and Social Entrepreneurship, an initiative of Tata Trust. He's also founded two companies, Design Alpha and Biophoton Technologies, and also supports as Chief Operations Head of Fox and Grips. Dr. Suresh has more than 150 publications, 18 patents, co-authored 3 books, and more than 200 technical reports to his credit. He has been conferred with many awards, including IEEE Outstanding Researcher Award, DST Lockheed Martin Award 2014 for the top innovation as ranked number 1 in India, BB Baliga Award, IETE Award, IEEE FGA Achievement Awards, to name a few. He is the chairman of many Government of India committees on R&D, member in various government steering committees like Ministry of Electronics and Information Technology, BSIR, etc. He is also in the project management group of Maker Village, member in Nidhi Prayas, DSP Healthcare Hub, etc. He is fellow IETE, distinguished fellow OSI, senior member IEEE. Dr. Suresh is currently chair IEEE Inter Council and is an active promoter of Academic Industry Association, is a member in university committees, and his passion is to mentor youngsters as entrepreneurs.
Thank you, Rehna. Over to you, sir.
Yeah, thank you. Thank you for having me in this FDP program. So, first thing is, like, I'm not a professor or anything, so I've been mostly focusing on practical aspect. So, I through this session, what I drive to all participants is, like, how can we make use of whatever we learn, whatever technology we have, and convert them to products, so that this will be useful for the society. So, before getting into the subject, I want to make things very clear. Whatever we are learning, so we are, all our education is subsidized heavily by the government, by the taxpayers. So, whatever you learn, and at some level, it is, you have to return back to the society. So that is what, of course, teachers are returning back to the society by educating the students. But in addition to that, you can also think of coming up with some products which can be used by the society. So that, with that background, what I will do today is, like, as I said, mostly on practical aspects because the other theory and all, you can always get it from internet and all. So my agenda is like setting the scene on optical wireless technologies. Then I will focus on fiber to the home. Then optical wireless communication, various areas, free space optical, visible light communication, optical camera communication. Then I think major portion will be my experience, a few case studies, where I'm talking about something to do with the optical technology, even though I have other things also, but here I will focus only on that. And I will conclude with that one. Okay, so with that, the background, set the scene is like wireless communication has, become an essential utility of our everyday lives. Even today, I think most of you may be receiving my talk over Wi-Fi. So everywhere it is required. Most of these wireless communication technologies use RF and like a microwave to convey information. There are many standards like Wi-Fi standards. I think you might have learned also that 801.11, ABGN, it is going on like that. Then LoRa technology, Bluetooth, 4G, 5G. I think 5G, yesterday you might have got a lecture on that one. So all these things are wireless. And in addition to that, you might have also heard about Industry 4.0. Industry 4.0 is like 1.0, Industry 1.1 was mainly mechanized thing. Like, you put the coconut and use a mechanical structure to take out oil and things like that, all mechanized thing. When Industry 2.0 came, it was electrified. For example, pumping, motor, using motor and all, you try to easyfy all those things. The third Industry 3.0, that is where at least my generation, that is mainly using computers. Okay, so a computer was used to ease out some of the things. But Industry 4.0 already started. That is on intelligent operation. What it means is like there will be a lot of sensors, and these sensors will be taking the data. This data is continuously analyzed so that you can predict the future. For example, just to give an idea about my expertise on manufacturing. Manufacturing equipments are very expensive, especially in electrical, electronics and all. So you can't buy one equipment, spare equipment, and keep it, because in case this goes bad, then I can use the other one, because we cannot really stop this manufacturing. So for that purpose, it is very expensive also to buy one equipment. So if you put some sensors in the existing equipment itself, the sensors are continuously sensing various parameters, and if this data can be used to sense that after some time this part may go bad, okay, so that I can immediately procure that and then keep it ready and also replace. So those type of things, I'm just giving one idea, one example, but there are many things. That is what we are going on. So a lot of data coming through. So all these data and sensors are there. They cannot be connected using wire and all. It will become very clumsy. Everybody is going for various type of wireless technology. So that's how it is going on. Then machine type communication for autonomous systems. You can see many of the cars are now becoming autonomous. So for that purpose, it has to continuously monitor, do many things, processing. Another like intelligent glasses using augmented reality and virtual reality, you might have already seen. I have seen a lot of startups coming up with these type of things. So where all these data, lot of data coming up, and you have to communicate. So in that case, RF spectrum will not be sufficient to future-proof wireless communication. Okay, so that is what we have to think. So we have to think of, can we get more spectrum? Okay, it is imperative to consider also the optical spectrum for wireless communication. I think those you have done some course on optical fiber communication, I think I have something here also. When the earlier, the telephone, whatever we are speaking, the audio signal, that is the modulating signal, the real information that is put on a carrier, that was a microwave RF, then it is sent out, and then, at the other end, it is detected and only the information is derived. Then we were thinking like, instead of that, low frequency modulating signal, can we use microwave itself as a modulating signal? Then the carrier has to be very high frequency, so that is an optical fiber. So can we put this microwave, RF and microwave on optics, send it, that will carry it, at the other end you detect and get back the information. So that's how a lot of development going on, because every day we are not very satisfied with the bandwidth. Okay, I'm not getting into this electromagnetic spectrum. I think you are all professors and lecturers and all, you know about that one. So what I want to show here is like, the frequency, when the frequency is 10 power 2, that is 100 hertz and all, it is that, those are all being used for the normal communication and all. Then when the frequency is going high, you reach radio waves, then you reach microwaves, then you reach infrared, then you reach all other ultraviolet, X-ray, gamma rays. So what it means is like, we are not really getting on to another domain. Normally, you can see that I'm not an optical person, I'm an RF person, okay? But you can see in the spectrum itself, when the frequency goes up, you are reaching that stage, okay? So it is all same. So it is not difficult, those who are working in wireless or normal communication area, to get into the optical area. That's what I just wanted to show here, okay? This is what in the new era, thought itself will be transmitted by radio. This was told long back, and this is what is happening now. Let me start with a very basic thing, even though you know all these things, but to set the background, this is required. As I explained, the modulating signal here, the information that is given into a modulator, the carrier signal, that is sine wave, where the frequency is very high, that is put, then you modulate, multiplexing type of thing. Then, normally in a system, practical perspective, the carrier signal is called as local oscillator signal, LO, local oscillator signal. The modulating signal is the normal information signal there, audio, or it can be even higher than that one. Then the modulation happens and you transmit that one. At the other end, the reverse happens. The modulated carrier is detected, then you demodulate, detect it, then you get back the information. So basically you want on both sides information sent and information received, and the carrier is just in between. Okay, so that is how it is done. And I think you know about amplitude modulation, frequency modulation, and all those things. But when we are looking at the local oscillator signal, you need to normally use very stable signal with very good phase noise. That's why I put this slide. Very stable signal. That means using a voltage controlled oscillator, you can of course generate a signal, a carrier. But this has to be phase locked with some stable signal like a crystal oscillator or temperature controlled crystal oscillator. That's where the phase lock oscillator comes, and then you synthesize and lock it so that the VCO, the output, will be very much stable with very good stability as well as very good phase characteristics. Then, if you look at, then people went from, or people started developing an optical fiber communication, and this is already a key enabler for the global internet. You can see the globe is connected using optical fiber cables, underwater cables, that is cable, submarine cables and things like that. That's how we are all getting connected, okay? It's not like always you can use wireless, because there are limitations because of the curvature of the earth also. Even if you have a line of sight, you can have maybe probably 14 kilometers or something like that. Okay, otherwise it will go, it will not go to the, due to the curvature of the earth. So people have realized that optical fiber is required to communicate between continents, and they have already laid down, and that itself is a very good area. And these are not only just connecting continents, they also form the backbone of modern communication networks. Whatever communication you are using now, the backbone, normally it is all optical fiber now, because that is where a lot of information can be carried, data rate can go high like anything. So that is what is done here. let me get on to the optical fiber, little basics only. Here what is done is like whatever analog information, whatever you have, the earlier telephones and all, the digital information, whatever you have the data, these are all put on a light source, a transmitter circuit. You might have seen that for laser diode, there is a characteristics, we have characteristics there. For digital, you have to bias at some place. If you want to have an analog also to be biased, for example, you want to put some RF signal on the thing, it has to be very, very linear there. The characteristics has to be linear. So that biasing points change. For digital, normally we bias at the king of point like this one. And for the RF signal, you bias at the linear portion. That's where you can get back all the information. So that is, everything is put on the light. It goes through the optical fiber cable. That is like light, you are guiding it. I'm not getting into the characteristics of a fiber optic cable, you may be knowing. Then at the other end, you are detecting. So light falls on and the electrical signals are generated. Then you amplify. Then you may have to shape it because some of the time, sometimes the digital pulses are not in good shape. So you have to, then you get back whatever you have sent as a digital pulse there. Then you decode it to analog signal as well as digital output. So that is a simple optical fiber communication. Then if you are having a connection, a fiber connection, that is called a fiber to the home. So here, what is being done, I want to explain this also. What is being done is like there is a central office where the voice, the internet, as well as whatever TV. These are the three things what we normally use it, using communication. So voice and internet are put through optical line in face there, terminal there. So you can see that is put together. You can see there are wavelengths used for these purposes, that is 1310 nanometer as well as 1490 nanometer from office to the customer side. Okay, then the TV signal, what is there, that is put on and it is amplified using erbium doped fiber amplifier, and that is at 1550 nanometer. These two are multiplexed, wavelength division multiply, because these are all put on different wavelengths. Then you can multiplex it, then put it together. Then you come here, that is, so all the things are there. Voice is there, internet is there, TV is there. It is going through one single fiber, multiplexed of course, and then it is split into N. Okay, because this is for normal broadcasting type of thing. 1 by N. N goes up to 16, 32 and things like that. And from each fiber is taken to your home. So a fiber comes to your home, and if at your home, if you see, there is something called ONT there, optical networking terminal there, which converts whatever light, the information on the light into back to voice, internet and TV. It is like a demodulator. So that is what is done. Here, since we are also using internet, you need to have two-way communication. Okay, that is what, from home, the communication go through 1310 nanometer. And you may be knowing why 1310 and 1550, there are specific wavelengths. There are many reasons for that, because optical fiber is made out of silica fiber, and this silica material has got a property. When you send all the wavelength, the less attenuation is given at a specific wavelength, that is 1550 nanometer. Then a little bit more attenuation is at 1310 nanometer. And 1490 comes a little bit more on attenuation, 1490 nanometer. So these are the low attenuation afforded by the silica, the material of the optical fiber. That is why it is made like that. And also the sources can be also realized at this wavelength. So some of the wavelength you have not really realized a very good source. So that is why all these things are used. Why low attenuation in the optical fiber means like the signal can travel more distance. That is the whole idea here. So that is how the fiber to the home works. Why I mentioned this one is like, this is a theory. So long back, maybe I think around 15 years back. Now we are getting fiber to home, but this idea was there at 15 years back, and I was also one of the contributors in the initial stages. This was very prominent in Japan as well as USA. Okay, India, nothing was there at that time. So this fiber to the home was just emerging. Lot of issues were there. So I am going to cover how, from my team, how we solved some of the things. That's what fiber to the home is already known, theoretical, no problem. But how we came up with some of the products, some of the solutions. That's what I want to focus on this one. Before getting into that one, you might have seen already I was in a government research for 13 years or so. You know, publications and all those things. So I was worshipping Saraswati at that time. Then, you know, when you move to industry, your mindset, I'm not talking anything religious here, but, you know, the mindset has to change. You have learned something, you know the theory, how can we make it convert into a commercial products? It is commercial product. Lakshmi means not only making money, but it's a service to the society also. You know, not the money making is not the only thing. You always have a thinking like industries are making a lot of money, but they are investing a lot of money, and that's how you know, we develop a lot of products. So that is how I was. My mindset has changed. So I also want you. I think you are all in the Saraswati side. So you just think. You know, whatever technology, you might have done some PhD in some very good areas. Can we convert that into a product? It's not to make money, to serve the society. So that's what it is. So here you can see I still believe in women empowerment. Let me get on to the subject now. So I put that one is like, you know, you have to listen to me also. When we talk only about subject, you know, people just switch off camera and do something else. So I was talking about fiber to the home. Then the requirement was a fiber to the home system has to be developed first time in the world. It has to be developed 15 years back. And we were focusing on multi-dwelling units. Multi-dwelling means multi-rise building. That is where we were focusing. We cannot focus everywhere. So there, this requirement was there from US. It's a company called Verizon, you may be knowing. They are very leading in communication. So we were invited there to, you know, they showed us what their requirement is. And you can see so many products we have come up of our own, which were non-existing in the world with a lot of innovations. I'm not, you know, if I have to explain all these things, it will take a lot of time. But still, I wanted to show what is innovation, how we came up with the innovation. You can see that requirement was like, you know, the fiber comes and every apartment has to have another fiber connection from somewhere common place. So what was done is like you can do splicing, like to take two fiber, heat it, and then, you know, you can splice it. But that will take a lot of time if you want to give connection to all these buildings. And in US and all, the manpower is very expensive, the technical manpower. So it was becoming very, very economically non-viable and very inconvenient and things like that. So they asked us, can you come up with a system, a solution where easily you can connect? You can give connection easily without expert technician. That was one of the things. So we came up, you can see here, JP is from Japan. I don't want to tell who has come up with. So all these people were called. Japan, people from Japan, US and India. India, we were there. So we called, they asked us, okay, this is my problem. You come up with a solution so that this can be used in a multi-dwelling unit or a multi-rise building. So you can see our you know, device here, your system here. I'm showing only one part of that. That is designed in such a way that innovation was stopped. I'm just talking about Indian innovation. So if we really put a lot of effort, you see how Japanese have come up with. They have come up with very good this thing, but the cable was lying outside. And US also something similar to that. Cable was lying outside because keeping the fiber inside is something very, very, very difficult. So you can see in our case, all the fiber, everything is inside the box, so that it's very safe. Nobody can cut the cable. You know, some people wanted to cut the cable and things like that. So that is not possible with a lot of innovation. You can see the performance also. when Japanese and US people came up with the 0.5 dB insertion loss, we have come up with 0.3 dB insertion loss. It took a lot of days and nights. It was a challenge for us. So the return loss is 65 dB we have come up with, where others have 60 dB. That means the reflected back. When you connect some light, how much is reflected back? So less reflected back is better. That's what we have achieved. So you can see here, this is the solution from requirement to solution, understanding fiber to the home theory. So this is how we have come. You won't believe we might have done a few hundred crores of business using this one. So that's what it's a very, very tiring one. A team with maybe around 50 people work day and night. And that's how I was going to US once in 15 days to show whatever development we are doing, like some prototype and things like that. So I just wanted to emphasize, if I just learned fiber to the home and left like that, in industry we will not grow. So you have to also, my motivation from my side is you have to also think in this way, and an academic can always come up with this one. We have a lot of public patents, on these things, US patents. One more thing I just wanted to talk about innovation, because this is also fiber. This is like, the telephone exchange near to your building or on the road, you can see these type of thing. That is where if you want a connection, the lineman will go there and connect the wire there. That is where it is called a distribution hub. Similarly, on fiber also, this distribution hub is required somewhere basement of a multi-rise building. So this also came to us saying like, oh, can you come up with a very good innovative solution? Innovative solution means it is not in terms of feature also, it should be cost effective also. So everybody, what they did was other customers in Japan, US and other places also, they have just mimicked the remaining electronic telephone exchange distribution hub. That is what, if you want to give connection, you have to access the back side also and front side. That is what is required. So if you take a plate, put all these connectors here and put a hinge here, and just to open that and you can access like a hinge, you can do that. So that was the solution given by everyone. If you look at our solution, the last one, the hinge is not there. There is a central pole here. You can see a central pole. So along with this central pole, this will move like this. It will rotate. So the innovation is like, this will never come out of the enclosure. So in this case, other cases, when the hinges are at the end, and if you open, it will come out of the enclosure, okay? But in our case, it will never come out of the enclosure. It is a very good new design. And it can do all the things what this can be done. This can be installed in snow, fog, rain and all, because water will not fall on this one. So that is how a lot of other innovations are there. This is another one, what we have done on fiber distribution hub, okay? Now the core area of today's thing, why I have told that one is like fiber optical communication was going for quite a long time, and we have also contributed a lot on that. But when it becomes optical wireless communication, means like, this is a wide range of optical wireless communication technologies are there. As a result of many use cases they can serve, because depending on the use cases, the requirements, you have to come out with, okay? Basically, in optical fiber communication, as you have seen, the optical light is going through the optical fiber because that will guide. But in this wireless means there is no optical fiber, that is the atmosphere, or there is nothing in between atmosphere or air, whatever you can call. Through that it has to pass through. So that is the difference, okay? The major technologies, one is the free space optical communication, FSO. The second one is visible light communication. I will come to each one of them. VLC, it is very much known for quite a few years now. Third one is optical camera communication, because a lot of cameras being used, and can you use that? The fourth one is wireless networking with light, which is also referred as Li-Fi. You can see now like Wi-Fi, wireless fidelity. Similarly, Li-Fi is also coming up. So all these things, I think Wi-Fi I have not put much, but I will explain that also here. Let us go one by one. The FSO communication is the closest functionality to optical fiber communication, as I explained. It provides static wireless point-to-point communication over relatively large distance up to tens of kilometers. So you have one terminal, another terminal you want to connect, you can either put optical fiber, but putting optical fiber is not very easy. I will come to that also. And this can be replaced with a free space communication between 2 points. So you can see here in this picture also optical fiber communication infrastructure is there, but the red color things are all free space optical. For example, from satellite to satellite you can have, then satellite to the aircraft to the ground station you can have. These are all mainly used in various applications here. Okay, that is what it is being primarily these FSO systems use infrared spectrum. That means you will not be able to see with your naked eyes. So that is what is being used there. Okay. Now let me take. You may be asking why all these things are required. Why don't we just bury more fiber, and all? It is very reliable. Okay, but the cost is very, very high. If you want to put, it has to be rodent free. For example, I have an fiber to the home at my office here, and I think 1 month back it was off, and when I found out the fiber was eaten by rat somewhere there in the duct. Okay, so that is there. There are many other fibers which are all rodent proof. Those are all expensive, but this is very expensive. Rights of way, that is very, very difficult to get. If you want to lay down some of the fiber, you have to get approval from various agencies. We ourselves don't like if somebody digs the road, we hate that one. And permit you have to get, trenching you have to do, time, all those things are required. Time, if you want to connect between 10 kilometers, you know how much time is required. But with FSO, free space optics, through the windows itself, no permit is required, no digging and no fees there. So this is how it is done. Very narrow and directional beam. From one place you are just shining. It's like putting a torch, to the other place. But it is very beams with very narrow diameter, very close spacing of links without interference. That's what you have to have if you want to have many. You can have some repeaters also. No side lobes, highly secure. This I will come later on. Highly secure is another important thing. I will come to one practical application. When we talk about optical fiber communication, as a teacher, you also must be teaching like it is the safest, secure communication compared to normal copper or wireless, because all those things can be tapped. But if you are sending information through optical fiber, it cannot be tapped. That is, you teach like that, but I will come to another area on that also. Efficient use of energy ranges to 20 meters to 4 kilometers possible, because there will be a lot of obstructions otherwise. Okay, that is the simple thing. Here what we are doing is the source, and same thing what I have shown earlier. It is modulated, it is driver is there so that enough power is generated, then it is put on the laser diode, then transmit optics. You like the RF you transmit using antennas. Transmitter is there, but antennas are there. The antenna is basically an impedance transformer, you may be knowing, because the transmitter system is of 50 ohm or 75 ohms. The free space impedance is 377 ohms. So you have to match these 50 or 75 ohms to 377 ohms. So antenna matches that very well, so that maximum energy is transferred. Okay. Similarly, in optical way, you have to have some sort of a lens. Then only you can transmit at a particular beam width and things like that. Is what is done. On the receive side, it is the same way. The light is coming, it is put on a photo detector. Photo detector will give electrical output. Then you demodulate. Then you take out the whatever data you have. So you can see in many of the buildings, You can see these type of FSO transmitter and FSO receiver. If you want to communicate between two top price building, it is very, very easy. Okay. Otherwise, you can use, the antennas also, some of them are available, but this is very good. But there are some challenges here. The data bandwidth is very, very high, but there are some challenges like is, some clouds and all. If it is very high rise, let us forget that. We don't have obstructions can come. For example, some crane movement when somebody is building another building. Atmosphere, fog, and scintillation can also reduce the range. Then window attenuation, where there will be a window where you are keeping inside, so that also, and all those things. Another thing is like when the sunlight comes just opposite to the transmitter, then also sometimes it gets, the signal goes, gets saturated. So those are some of the things what is being done. So that is on the free space optical communication. It's very widely used. Okay. You can see in many high-rise building, people are using that. And it is very easily installable. Just put the thing here, go there and put that one, there your communication link is established. The next one is visible light communication. With the advent of blue light emitting LED, LEDs, and also bright white LED, visible light communication has come out. So that is like using visible light, can you communicate? That is what. The first VLC application which used white LEDs was wireless audio signal transmission. In our lab also we did this one long back, visual light communication. Like, for example, you have LED lights and all. So you can send your audio song, for example, there. And if you put a photo detector here and put a earphone, you can hear the song from this light. This is very much easily you can make it. I think a lot of BTech students also have come up with this type of thing. So in our lab, what we did was like there were a lot of product demonstration we put in. So the visitor, when they come, we had to explain all these things. Instead of that, we give an earphone to the visitor. So when they stand below a particular product, the light is modulated with the information about that product. So you need not really explain. So when you stand there, they will be able to hear about that product, what otherwise normally we will be explaining. So like that, when they move to the next one, so they will be able to. So this is very easily you are able to do. And visual light communication in a broader view, you can see, you can use for various driving the smart devices, you can use some of the desktop, you can use it printer, like Wi-Fi type of thing. You can use it plant, whatever you want to use it, HDTV, all these things. In a room, you are able to use it, but you need to have a lot of LED lamps there. So that is not really very, very interesting compared to Wi-Fi. Wi-Fi means you can carry your laptop, move around and then get. But here, the light is required. So that is one major thing. People are trying to solve it using some scattering and things like that. The third one is optical camera communication. It's a similar way to how high brightness LEDs have led to VLC. The digital camera in smartphones has led to optical camera communication because it is possible to use this sensor to detect information encoded in flickering light. This is like a simple example if I want to explain. For example, when we are standing for a few minutes at the traffic light, if the traffic light is modulated, the red light is modulated in such a way that some information is given to us, and those who are sitting in the car or vehicle will be able to get those information, from that, saying like, there is traffic after this junction and things like that. So whatever information you want to convey. So that way it can be done. So this is going on in a big way, but this is not only for this type of communication applications, for many intelligence. I will cover that in my case studies. So these are also being used. So example, I'm just seeing like, V2V, vehicle to vehicle communication, you can use it using the traffic light, augmented reality, you can see it's many applications are there. In camera based positioning, you can find out where you are. Then with the interactive screen also you can, you can select using some of the gadgets so that you can select the menus which are displayed. So many applications are there in that. So the development came because of laser device. Laser, when I talk about laser, laser diode is little expensive compared to LED. But there were VCSELs coming up, vertical cavity surface emitting laser. Otherwise, laser diodes are edge emitting. Like, you have to keep the laser bar like that and it will emit like this. So like that. But for many applications, it was not very good. So that people came up with VCSELs, vertical cavity surface emitting lasers. This is working in infrared spectrum, and this is mainly used for these type of OWC, optical wireless communication links. So when this came up, it is very easily manageable. Like LED, you can manage, because laser diode and all, you have to give a driver, you have to take care of the temperature, because when it is lighting up, it gets heated up. You have to control the temperature, otherwise the wavelength will shift. All those things are there. Okay, and inorganic semiconductor devices are also coming out, which can be, for example, bent. Okay, so that they're all very good for these. They flexibly. For example, you want to have an inorganic, detector, so which can be made as a flexible round and things like that. So all those things are making this area grow, and a lot of research is going on in this thing. The advantage is like gigabit per second and all, easily you can achieve. Even if you are able to get 100 Mbps, your link is extremely good. You can think of gigabit per second, there will not be any issue. You can send video and things like that. So we are not at all happy with the communication it is now. And every day we are looking at how can we improve the data rate. So that is why all these things are coming up. A few more challenges are there. Optical system is to ensure eye safety. For every infrared, ultraviolet, they are all not good for eyes. Okay, so when you are designing something, for example, you put two infrared transmitter receiver, nobody can see. That doesn't mean that you can fool people. You have to take care of all those things, eye safety things, so that, all those things you have to really take care of. It is like wireless also. I'm really worried. So much of devices in our room also, you can see maybe some 10-20 devices are here with wireless connectivity, and all are transmitting RF signals. I don't know what is the effect on us as a human being. Even though there is SAR limits defined, so within that limit there is no issue. But I'm not very convincing on that. Similarly, in optical spectrum also, this is an issue. This can be a challenge when the transmitter is a point source, because a lot of power is coming out. If you have a spread out source, then it may be better. But in this our application, that is not possible. So it is often desirable to convert the point source into an extended source, which changes eye safety condition. Otherwise, even laser beam, if it comes, you can become blind very soon. So all those things, a lot of research is going on, and this I will just leave it. So it is like optical frequency division multiplexing. Yeah, that aspect I have to cover. See, normally 1310, earlier we started with 1310 nanometer. Our bandwidth was not sufficient, as we made a lot of application. People found out 1550. Then we put together 1310 and 1550. That is called wavelength division multiplexing. That is also, we felt like it is not sufficient. Then 1550, we separated into many dense wavelength division multiplexing, DWDM. Like near 1550, can you take another spectrum, 1551, another one 1552, or 1550.8, and like that, many carriers. Then put on each one of these carrier the modulating signals. Then you send it so that you will get the data rate very high, multiplied into whatever number of carrier you have. So all those things were going on. But similarly in this also, orthogonal frequency division multiplexing is now coming up in this area, where you use inverse fast Fourier transform to send transmitter during the transmit side and the reverse fast Fourier transform at the receiver side. I think you may be knowing about FFT and things like that, what we are doing. Now coming to my experience, these are all case studies. I'm not going to share the slides, so please listen. And all other what I have talked about earlier was most of them are available in internet also. Let us get on to some case study. This is very interesting. I hope it is very interesting for you what we have done. Like earlier I explained fiber to the home, what we have done. Okay. In a standard textbook on fiber optic communication, if you read, data security is one of the advantages of fiber optics. I think that's what you also teach. That is like you are sending the optical light through an optical fiber, and it is very safe. That's why in military application and all this is being used, optical fiber communication used. Otherwise, if you use a telephone line, in a normal copper, if you parallelly connect, you can also listen. Otherwise, wireless, if you put a receiver, a wideband receiver, and then you detect it, and there may be a possibility of listening. Of course, there are, as an expert, some of you may be expert in code, like what is it called, data security and all. So you may tell like I have some protocol to send so that I will put some key on that. Without that key, you cannot unlock and listen. All those things are there. But our idea here, I will get on to that. Fiber optic cable networks, they are the fastest, more reliable. This is not very safe. This data, when you are sending over optical fiber cable, also is not safe. This is come out after some time. I think this also maybe around 15 years back, 10, 12 years back. We realized, actually, I came across saying like there was some, what is it called, intrusion on optical fiber network in sea, that is submarine thing. So some country went and opened up that, and they were intruding into the optical fiber network. So at that time only we thought like, is it possible? This is possible. It's not like we have come up with a theory. It is possible. I will just go to that. So think of the situation. You are sending very vital defense data using optical fiber, and somebody is intruding and listening that one, then it is very, very dangerous. Similarly in banking, a lot of information goes through the banking thing, and if somebody is able to take the data, manipulate the data, then it is very, very dangerous thing. So that is why we thought like there can be an application here. Okay, why I'm explaining all these things in detail is like, if I also might have thought like they believed the textbook saying like the optical fiber cable is the safest and leave it. So then this product would not have come out. So we have to always think, are there any other way to intrude this optical fiber cable? Then if you take an optical fiber cable, normal cable with plastics, okay, give some laser light, whatever we use for slide presentation, you just bend that fiber, you can see that corner will get lightened up, like red color. If you are using red LED here, laser here, then you can see that bend. If you make sharp bend, you can see that light coming out. If a light is coming out of the fiber cable by making a bend, that means you are able to take out, if you are able to detect that light coming out, a little light coming out, you can detect that, you can intrude the data. So that is the whole idea here. Okay. So if you are able to take a fiber cable, and if you have instead of bending yourself, if you have a mechanism to bend, make some particular bend using some external force, then you put a detector to take out whatever leaked out light, and then detect that one, decode whatever you are doing on the normal side, and then you can get it. So this is one of the idea which we got it, and this we call it as a, there was a clip-on coupler at that time available also. That has got another application, but we thought like this can be used. But we are not really basically an intruder. So what we want to do is like, what is the solution to avoid that one? Okay. You may ask one thing. Okay, if somebody is intruding, there will be a loss introduced, and then I will be able to come to know that there is some loss there. Then my link may go bad. So then will you be able to detect that one? Okay, that is your normal question. I will show with one example. Normal link, a transmit power, I will assume like -5 dBm, and your receiver at the other end, it has got a sensitivity, how much power it can receive, minimum power, that is -34 dBm. These are all typical values. Then I will assume that the link loss, there will be a fiber that loss from one point to other point, let us take 19 dB. Oh, that is a maximum. Now, if you see -5 dBm you are sending, the link loss is 19 dB. That means the other end you are supposed to get -5, -19, that is -24 dBm power. -24 dBm power you are able to get normal. But your receiver will work even if it goes down to -34 dBm. Okay, that means -24 to -34 dB, that is 10 dB margin is given in the thing. Still, your system will work. So that means even if a vehicle goes over that one, it may introduce 5 dB, still your system will work perfectly. Okay, unless you introduce more than 10 dB loss by some way. But the bending and all, there are equipment you may introduce 0.1 dB loss by bending. There are equipment for that one. So you introduce only a very little loss, but still you are able to get intrusion. But your transmitter and the receiver, the customer will never know that this is happening because their system is working perfectly. So that is very, very, very dangerous thing. Okay. So by looking at any loss is happening, you cannot make out whether somebody is intruding in the network. So what is intrusion? For example, a server is there. I'm a client. I think the line has broken. Just there was some problem when I copied it. So when a client is, if I go back, when a client is asking some data, it can be voice and data. So it goes through media converter and gets a client, but using a clip-on coupler in between, a copy is also going to intruder without the knowledge of these people. So this is very, very dangerous thing. So what we have done, as I said, we are not intruder. We have come up with an idea where you can detect any intrusion in an optical fiber network. That is what we have done. I'm not getting into all these details, and I will not be able to explain much because currently our Indian defense is using our system. So why I'm showing this is like, if I have also thought like optical fiber is safe, nothing happens, this system would not have come. Now we have developed a system. It took a lot of time, but we developed a system. You can safeguard any optical fiber network. It can cover, I think at present, it can cover around 80 kilometers. And if anybody does any sort of intrusion, for example, the optical fiber cable is not very simple cable, whatever is laid down. It has got a lot of layers. Okay, even then, if somebody is, touching that cable, hitting the cable, for example, if you want to access the cable, somebody will use some, to dig some place so that you can take it, that one, it will be able to locate, it can give alarm with location accuracy. So if somebody is trying to cut the outer layer, immediately you can get an information that this is being cut. Then if somebody is taking any confidential data, immediately you will get. Then you may ask, what is the advantage? So we have designed the system in such a way that as soon as somebody is doing this type of activity, like started digging using JCB or time to cut, immediately that data will be rerouted through some other geographical path to the other system. That means the customer and the server and client will not realize that this has come. This information will go to authorities, okay, but the system will be working through other redundant network. That is how it is planned. Why it is done is like, and also we do some more thing, like we will send some junk data through the affected fiber so that the intruder will be thinking like that will be the correct data. They will continue to be there, so that we can physically go and catch and things. A lot of strategies we have planned. This is one system what we have already done. You can see it is called intrusion proof system. It is already 24/7 monitoring, and 65 now we have come up with 80-kilometer range. Alarm, everything is there. You will be so, and the satisfying thing is like many such systems are already there in Indian Defense Network. So if anybody touches our network, you'll be able to find out that. So that is one example. I am, as I said, optical fiber communication, where this is one of the major applications. Let us now get on to more experiences. The fluorescent, the wireless thing, there are not many things like RT-PCR and things like that. Using fluorescent property of the sample, you can do many healthcare related activities. That's what we have been doing that, and I'm not getting into all these things, but we used around various wavelengths, including 480, 490 by 525, 530 nanometer, and all those things. That is the emission. Fluorescence means you supply with some wavelength and the emission will be different wavelength. So you take out that one, all those things. So using these most of them are wireless here, and you apply some light, and there will be a lot of sample. For example, in RT-PCR and all, there will be a lot of samples simultaneously loaded. For example, 12 sample. All these samples are put in vials there. So we have come up with a system so that from common LED, that light, same LED at particular wavelength is taken to and split, and this light falls on every sample, and the other side of the sample we have put a detector, and based on the detected signal we will be able to characterize the sample. Okay, so this is what we have come up with. From that's a theory how to come up with the device. So that's how it looks like this. You put all these PCR tubes and all there, then you can get, after the processing, you will get the information here. So that is what we have used in these wavelengths. Another interesting application, again wireless, is like a breeze scan, what we have come up with. I think I might have explained these earlier sessions also, but for sake of completion. See, this light has got a lot of research application. That's what I wanted to emphasize. Here, now let us take cancer. Cancer is one area where a lot of such applications are coming up, a lot of scope for research. Normally what is done is like, a lot of cancer happening, like breast cancer, then oral cancer, cervical cancer, and things like that. In India, I think oral cancer is the top in India among men. Breast cancer is the top among women in India, and cervical cancer is also, I think, the second one for women. And once the cancer comes, normal thing is like we don't really realize that we have cancer. We will go on extending, and at some stage only we will realize it is very difficult. So we go to the doctor, and then by that time we might have reached third stage, fourth stage, and all. then doctor will take out some sample and send for biopsy, okay, and it will take some time to get the results, and then the treatment starts, like chemotherapy and medicine, surgery and things like that. So in cancer, what I believe is like early detection is the cure. That's where people are now moving. Everybody is moving towards that. Why we are not able to detect at early stage? Because we are not going to a place at the earlier stage. We don't have a place. We don't know where to go. If we go to cancer center, so much of crowd is there, and it takes a lot of time, and for normal thing you don't feel like going there also. So that is why we were thinking. Now, taking biopsy is another thing. Like, it is painful, and it has to be done in a proper way. So, doctor will examine and do incision and take out the tissues from suspicious areas, then send it for histopathological examination. It is painful. Multiple biopsies you may have to take. It takes days to get results also. So we were thinking, like, is there any way using light, you shine light at particular wavelength, shine light at the oral cavity. At that time itself, are you able to get some information of the normal thing? In that case, this can be done at primary health centers or normal dental clinic itself, because they have to just shine light and understand. If they feel there is some problem, then only they can refer to cancer centers and things like that for other things, and it is very easy to treat during the initial days. So that is what we have come up. One of the techniques, there are many techniques. One of the techniques which we focused was diffuse reflectance. Instead of getting into all these things, you shine some light, the light gets into the tissue, and the property of the light changes depending on the tissue. If it is a healthy tissue, something happens. If it is like a cancer tissue, something else happens. Maybe something else means mainly we are looking at a few factors, few properties of light. Example, how much absorption happens, how much, in some cases, even wavelength changes. So all those things we are looking at. So that is what we have done with our initial initiative. So we thought, like, it can go, see, normally the cancer, oral cancer specifically, it is on just at the surface and a little bit deep only, not very, very deep. So this can be used. So we came up with a proof of concept. We used a particular light wavelength. We came up with a small probe. We designed, we made it here. The central fiber, these are all fiber. From fiber, it is wireless. The fiber, central fiber is transmit, and around that we kept, I think, 6 fibers for receiving fiber. And there is a lot of design involved, because the receiving fiber should receive the light which has gone through the tissues, not the light which is directly coming out, like reflected light. It's a diffuse light, diffuse reflected light only we want it. So some design has to be done so that the directly reflected light is not getting into that one and saturate that. So all those things we did. Then we looked at the spectrum. We know what spectrum we are giving in, what spectrum we are getting, how much absorption happens, and things like that. So then we came up with a device, and we, when a device you are coming up with, it should be a small device, and we put everything, all these laser detector, everything into a small engine called light engine. That's how we designed. There was a patent also in that, and we came up with that down one, what you are seeing. This is an earlier version now. You can see there is a light at the probe. This cavity, if you show it, wherever you are pointing at the screen, you will get as a normal tissue, healthy tissue, or at what stage it is, early cancer or the cancer stage. That's how we came up with this one. And these are all engineering which we have done. You can see, it's Android, using Android, because you have to enter all the values, and this has to take all the values, data, keep it. It's all confidential data. Then we also came up with one screen which shows green, yellow, and red, and only doctor will be able to diagnose. So this is for screening purpose only. So this we did in various government hospitals and all for initial trials and things like that. It was very successful one. There were some competing technology at that point, but ours was very good. We did not take any tissue or things like that. So it came up in various areas. Oh, yeah, this is one lighting thing. When we came up with, I think in 2014 or so, it's still continuing. The paper said like we have come up with a system so that the whole body can be scanned. So that is how the media made it. But it was not like that only for oral cancer. I'm just showing a lot of, this thing we got approvals. The minister also came to see. Now, after all those things, we are now introducing, we have already introduced artificial intelligence also into this one. Because this is also very important to improve the specificity and sensitivity. See, now the era is like digital pathology. You take the data at some rural point, the data is sent remotely, and the specialists are looking somewhere or located somewhere else. They will be able to diagnose immediately. And your system can also have that lot of big data is there, is analyzed, the knowledge is built. From that knowledge itself, you can improve the sensitivity and specificity. Sensitivity means like if there is a cancer, it should detect. It should not forget to detect. That is what sensitivity. Specificity, if there is no cancer, your system should not tell that there is cancer. So that is also dangerous. Or there is cancer, your system should not tell that there is no cancer. So that is all these things, it is very dangerous thing because you cannot give wrong results. So you have to do lot of research. Not only in Kerala, we are from Kerala, we are from here, because the oral structure, the skin properties change from this place to northeast. Where people use the gutta and things like that, their things are changing. So all these things to be taken care of. That's what. So from that optical wireless, we have come up with a device which is socially very much useful. A lot of people are working on, and we are also working with a lot of agencies to come up with these devices. Let me get on to some more application. As I said, these are all mainly applications developed by us. One of my companies is Biophoton Technology. So here, those who are mothers, I think the mother who are attending, when a child is born, normally in many cases it gets jaundice, the yellow color. Then the child, new infant, is taken inside the NICU and put there under, these. What is it called? LED light. Earlier it was blue light. Now people have changed to LED light. So light shines on the body of the infant. And you can see at that time, the infant's eyes are, what is it called? Tight. So that the light will not fall into their eyes. It is dangerous. So that is what it was going on for years. So what we thought is like it is very inconvenient for the mother, new mother. New mother wants the child always with them. And the relatives will come to see and all those things. There are a lot of issues. And we found that the child, the infant is not very really comfortable there in the NICU. Only thing is like we are not seeing. The parents are not seeing. Only the sisters and all who are there inside they are seeing. And they will show the infant to the mother only for feeding. Okay. So we thought like, can we change that scenario? And we have some LED lights. And can we come up with a blanket? This is called a blanket. You can see here. So that the child can be wrapped with this blanket. That is what you can see in one of the hospitals. So that is what we have done. We use the spectrum 450 to 470 nanometer, which is with a peak at 450. And this is very effective. That is proven. But what we thought is like, how can we make it very comfortable? We used a blanket, and then from the blanket we made in such a way that the wireless thing happens. There is no blanket, there is no fiber there. It just radiates from there. That is a very good design which we have come up with. So that is what we have done. So that the child can be, the new infant can be with the mother always, because this is a small device which can be kept in the on the bed. So the mother is always at the with the this thing. So this we sold many. So I'm just showing some application. Another one is infrared light based vein viewer. Those who are working now, lot many people have come up with this one. Here I will tell the technology and close it. What is done is like when the blood flows and when you send infrared, the infrared gets absorbed differently by the blood, which has got a lot of oxygen and less oxygen. Okay. From that, if you are able to take out that infrared image, process it, and shine it back like a projector at the same place, then you are able to get an infrared vein viewer. So this is one thing which we have came up with. Another one is, another application is, nowadays it is very much used during COVID, but we came up with this little bit ahead of this COVID. If you look at your toilet handle, toilet seat, door knob and all, and look at your cell phone is more dirty. That is what it says. Okay, you don't really realize that. And you give this cell phone to infants, children will play with that because I have seen that is the best gadget now. The new generation children are using. If they cry, you just give it and it works on that. So we came up with, there are many sanitization devices available which are using the tube, the UV tube. But what we have done is we have come up with a system, this one, which is called BioSan because it is from Biophoton Technologies. And this uses LED UV, and you can put whatever you want inside, like your chashma, your mask, all those things inside. And it will automatically detect that and it will sanitize within 2 minutes. Okay. I think it gets at around 1.5 minutes, it will get 100% sanitized. We gave this device to Rajiv Gandhi Institute and did all the certification and all. So this is what we have come up with. This is very much useful for during COVID time. So just put it there. And the top portion can be taken out independently and you can use it if you are using any public toilet. Now, before using the toilet, you can shine it so that, it will get sanitized. So many applications are there. And this is designed in such a way that if the angle is around 45 degrees, there is an accelerometer put inside, it will stop the shining of this LED light so that it will not fall on human eyes when you use it. So all those precautions we have taken up here. Yeah, this I think I will skip it here for one of this thing. Then lot of applications are now coming up in vehicle-to-vehicle communication, B2B communication. When autonomous cars are required, every car has to really have some radar type of thing. So that is where a lot of RF plus optical combined things are now coming up. We have also developed one of the proof of concept for that. It is still in the initial stages because it has to go through a lot of validation. But a lot of application, if those who are interested in those things, you can just look at those. Another application which earlier when I was working there, we came up with the fluid tagging technology using same way optical wireless. For example, if I am having a water, okay, in water it is I am selling water, for example, drinking water, mineral water. I am selling that, and if I want to test that water, whether it is the water which I have, which is mine, original, then you have to do some test and all. So similarly, there are many applications like currency printing ink. Okay, currency printing ink. If we want to see whether this is the real ink government has approved, or is it something different, there is very difficult to identify that. So we were thinking, like, can we come up with a probe, a light probe, which when the light probe is shined on the liquid, and maybe many of the applications you can use maybe a fluorescence, so you can see what comes out, and you design the material, the ink, in such a way that there is a specific signature, so that you just put that probe inside and immediately you will know whether it's a genuine thing. It's just got a lot of application. I don't want to tell all those things, but you can imagine many applications are there. Where, for example, diesel, petrol, then ink, and like that, many applications. So we have developed one of those things, and this is very successful. So I'm just giving so much of products, so much of ideas you can come up with. This is the inside of that one, which has got an optical subsystem. There is a lens. There are a lot of control electronics and things like that. That's how we made assembled in a particular thing. This also underwater acoustic sensing system is also. I'm not supposed to explain a lot because this is developed for Indian Navy application. So here. You can, there are underwater acoustic things. For example, acoustic, I will just explain that when we are firing a torpedo, you must be thinking like the torpedo will get fired from the ship and it finds its own way and then goes and, bang with the enemy vessel. It is not like that. In underwater communication is not very easy. Okay, you cannot have long-range communication, wireless communication, underwater. Okay, so there are some communication available, but these are all short range. So when a torpedo is launched, the communication is through a copper wire. A copper wire is already tied with the torpedo and the mother vessel, and when it goes, the torpedo goes at that speed. The mother vessel unwinds that spool so that it can go like that. But the communication is always through these copper wire. Okay, so all the things like guidance and things like that. The mother ship guides that torpedo and finally it goes and kicks. That's how it is done. So then there was another one which we have done is like using the copper. We converted that to optical fiber. Optical fiber, some special fiber, which will withstand that much of pressure, underwater pressure. It can withstand, that biting by the whale and things like that. So it is designed in that way. So that way it goes. So we realized that type of torpedo communication through this one. So this, when the acoustic things, signals are there, because when other ship, enemy ship is there, there are some acoustic signal. So this system, this is a true wireless thing, optical wireless, you will be able to sense that. And so that is how, compared to normal transducers, optical sensors have got very good sensitivity and we have proven that. So with that, I think I should close that. We have also come up with optical amplifiers. These are also very important. Like your RF signal. When the RF signals becomes weak, what we do is we put an RF amplifier so that from weaker signal it will amplify to a higher signal. Okay. Similarly, in the optical case, what has been done earlier was like optical when it becomes very weak, that is digitally, electronically detected first. Then that electrical signals are reshaped. Then it is again modulated on optical. That is how RRR thing happens like that. Okay, receive, reshape, and then retransmit. That is what is done. That means the amplification was in digital domain, not in optical domain, even though optical signals are used. But some time back, people have come up with direct amplification of light. That is, one example is erbium doped fiber amplifier. That's a rarer material. If you dope the erbium in an optical fiber, then using another, so for amplification, somewhere energy is required. That is given by another wavelength called 980 nanometer wavelength. We call it as a pump signal. So you give that pump signal to the special fiber, give the low signal, our signal, that is the 1310, 1550 normally, then it gets amplified in the optical domain itself. That's what we have come up with these type of, so the inside thing has got all these things, systems like it input counts, then it is detected, it is amplified using the signal is pump signal at 980 nanometer, it gets amplified and it goes out. So that is what we have done in these things. So these are some of the applications. You can see if you open it up, it will look like that. The circular thing is the special fiber, but this is also made within India. So that is how the amplification happens. So with that, I think I have done a lot of special application. I am not getting into the theory part of that. You can always read it from internet. But these are some of the specific examples, what we have worked in healthcare area, in defense application, in communication area. So the applications are many. You will be able to, if anybody is doing any research application, then you can get all these things. You can extend all these things. You can see all these theory converted to practical products. They are not just prototype. They are all commercialized. They all have gone through certifications, and these are all supplied. They are all used in the field. So with that, I think I should close. Any questions and all, I'll be able to answer that.
Thank you, sir. The floor is now open for questions. Participants can unmute and ask.
Yeah, there was some question, I think, I think I have answered those things. How power is something by, power is, normally not the normal power, but high powers are being used. I have not covered that one specifically because, the laser beams are being used for various applications to shut down. And there are a lot of government agencies in India who are all working in these high power laser areas. I did not want to comment on that one, but those are some of the things, application. Yes. Very high power. It's very, very dangerous to apply or use it. Yeah, but only for defense application you can use it.
There is one question in the chat window. May I read it? It is how to transfer RF power by optical. This is the limit.
Yeah, this I think I covered that one. Yeah.
Next is from Anubam Tiwari. FSO attenuation is very high, only LOS.
What is that question?
Anubam, can you please ask the raise that question? It's not clear.
Let me just see. How to transfer RF energy, that I have explained. So these, RF power means, like signal. I call it as a signal. Okay, so if you take a laser diode, it has got the VI characteristics like, initially it will be normal and then it laces. So when a digital transmission is used at the kink, there, at that corner point, you have to bias. But for RF communication and all, you have to bias at the linear portion, then only you will get the correct reproducible thing. So that is what is being used now. So earlier RF was used as carrier, but now this can be used as a modulating signal, and the carrier here is the optical thing. BLC, I think a lot of research going on, like a few gigabit is also now possible. See, the visual light communication, one is like the street light. You have a lot of LED street lights. Can we use that for some information broadcasting to the people? It can give many things. So those are some of the application. Cost of these sanitizer is around 4,000 500 rupees or something like that. Then how power is on? Yeah, the power is, as I said, it is optical power we are transmitting, not the normal power. Normal power, I think people were using like optical cable. There are some cable where it can have a conductor also along with the cable, and through the conductor cable, it comes as a one cable, but this also can be used then. Okay. Thank you for the patient, listening.
Sir, you have a lot of appreciations.
Yeah.
And you normally get these appreciations. I have attended many of your sessions. Thanks for the informative session. It was a wonderful session. And as a token of gratitude on behalf of the participants, I am presenting an e-memento to you. Please accept that.
Yeah, thank you. Thank you very much. Thank you.
Thank you all. Thank you, sir.
Thank you.
So we'll have the next session at 2 o'clock. Feedback link is posted in the chat box. Thank you. Thank you, sir. Thank you once again.
Thank you. Bye.
Hello.
Hello, the feedback link is not attendance. It is not posted.
What happened? Feedback link is active.